In the vastness of space, certain events spark curiosity and wonder in the scientific community and beyond. One of the most captivating occurrences in recent years is the arrival of 3I Atlas, a mysterious interstellar object that has captured the attention of astronomers and space enthusiasts alike. Discovered on July 1, 2025, by the Atlas Survey team based in Chile, 3I Atlas quickly became an object of intense study. What set this object apart from others was its unusual origin. Unlike most comets or asteroids that belong to the solar system, 3I Atlas is an interstellar visitor, having traveled across vast distances from a distant star system. The discovery of 3I Atlas sent ripples through the astronomical world. Interstellar objects are extremely rare, and the fact that 3I Atlas is only the third confirmed interstellar visitor to pass through our solar system adds to its intrigue. The object was initially catalogued as just another comet, but follow-up observations quickly revealed something extraordinary. Its trajectory was hyperbolic, meaning it was on a one-way journey bound to escape our sun's gravitational pull after a brief encounter. The speed and path of 3I Atlas indicated that it had traveled from a completely different stellar system, making it a celestial traveler from the vast expanse of interstellar space. What makes 3I Atlas even more fascinating is its composition. Early observations using advanced telescopes showed that the object had a distinct green glow, a feature not typically associated with comets in our solar system. This peculiar coloring raised immediate questions. What was responsible for the green hue? Could this be a clue about its origins, or was it something completely unknown to science? As 3I Atlas entered the inner solar system, it began to reveal more about its mysterious nature. Scientists eagerly prepared for its closest approach to the Sun, scheduled for late October 2025. During this period, the object would pass through the solar system's Goldilocks zone, a region that is not too close, yet not too far from the Sun. This would be the best time for astronomers to conduct detailed studies of its chemical composition and structure. But as 3I Atlas came into view, another phenomenon began to take shape, something that no one could have predicted. Just as 3I Atlas entered the solar system, an unexpected surge of cosmic traffic began to unfold. Suddenly, the skies seemed filled with an unusual number of asteroids, comets, and other interstellar objects, all heading towards the Sun at the same time. This cluster of objects was no coincidence, and it set the scientific community abuzz with questions. Why were these objects suddenly appearing together? Was there a deeper connection between them, or was it simply a remarkable convergence of cosmic events? One of the most striking aspects of this surge was the clustering of comets and asteroids that appeared around the same time as 3I Atlas. At first glance, these objects seemed to be part of the usual cosmic traffic, asteroids making their regular flybys and comets brightening as they approached the Sun. However, upon closer inspection, the timing and trajectories of these objects appeared to be unusually synchronized. Was this a random occurrence, or was there something more profound at work? The object that immediately caught the attention of astronomers was comet C/2025 R2, discovered by the Solar Wind Anisopes instrument aboard the SOHO spacecraft. This comet had begun brightening rapidly towards naked-eye visibility and had a tail stretching across the sky like a celestial brushstroke.
The fact that it was discovered just days before 3I Atlas entered the solar system raised suspicions that the two objects might be related. Could 3I Atlas, with its bizarre trajectory and chemical composition, have had some effect on the orbits of these other objects? Astronomers soon realized that this wasn't just about a comet or two making a routine visit. Instead, it seemed that a swarm of objects, comets, asteroids, and other near-Earth objects were all showing up at the same time, each following unique paths, but all converging around the same period. As if by some unseen force, these objects were drawn to the same point in space just as 3I Atlas made its historic approach to our Sun. This unusual clustering was a puzzle that required further investigation. As astronomers continued to track the trajectory of 3I Atlas, they began to consider a hypothesis that seemed increasingly plausible. Perhaps 3I Atlas was playing a role in the appearance of these other objects. Could it be that 3I Atlas, as it passed through the solar system, was gravitationally perturbing the orbits of nearby comets and asteroids? Was the interstellar object somehow influencing the paths of other celestial bodies in the solar system, triggering their arrival during the same period? Gravitational interactions between objects in space are well known, but the scale and nature of the forces involved are usually minimal. However, the fact that 3I Atlas was traveling at such an immense velocity and on a hyperbolic trajectory suggested that its gravitational influence could be more substantial than previously understood. Was it possible that the object's passage through the solar system was pulling other objects into its wake, like a cometary train of cosmic debris? To explore this possibility, astronomers began examining the orbits of the objects that had appeared around the same time as 3I Atlas. They quickly discovered that some of these objects had trajectories that seemed to align with the path of 3I Atlas. In particular, several comets appeared to be arriving at similar points in their orbits as 3I Atlas, as though they were responding to the gravitational forces exerted by the interstellar object. This was an exciting development, as it suggested that 3I Atlas could be exerting a force on the solar system's small body population. If this was true, it would have profound implications for our understanding of how interstellar objects interact with our solar system. Could 3I Atlas be a kind of cosmic messenger, triggering a chain reaction of celestial arrivals and influencing the evolution of our solar system?
Movement of objects in the solar system. Or was this simply a rare coincidence that had no deeper meaning? As scientists considered the possibility of 3I Atlas influencing other objects, they began to develop theories to explain the phenomenon. One of the primary questions was whether the gravitational pull of 3I Atlas could be strong enough to alter the orbits of nearby comets and asteroids. Given that 3I Atlas was traveling at high velocity and on a hyperbolic trajectory, its gravitational field should be weaker than that of more massive objects like Jupiter or the Sun. However, the speed at which it was moving and the large number of objects arriving in its vicinity raised questions about the role its gravity could play. Some scientists speculated that 3I Atlas's arrival might have caused subtle shifts in the orbits of nearby objects, pulling them into the solar system or altering their trajectories in ways that hadn't been predicted. Others considered the possibility that the electromagnetic fields surrounding 3I Atlas, which were unlike anything seen in our solar system, might be interacting with nearby objects in ways that were not yet understood. Could 3I Atlas be emitting radiation or other energy forms that were affecting the behavior of these other objects? While these theories were speculative, they presented intriguing possibilities. What if 3I Atlas was more than just a gravitational anomaly? What if its composition and energy were interacting with the solar system in ways that defied current scientific models?
These questions led to more detailed studies of 3I Atlas's electromagnetic emissions, as well as its effect on the surrounding space environment. As scientists speculated about the role of 3I Atlas in the surge of new arrivals, they also began considering a more fundamental question. What happens when objects from different star systems collide or interact? In our solar system, most objects have been bound to the Sun for billions of years, following stable orbits. But objects like 3I Atlas, which come from other star systems, are traveling at high velocities and following trajectories that are not influenced by our Sun's gravity in the same way. Could the interaction between 3I Atlas and the objects in our solar system be part of a larger cosmic cycle, where objects from other star systems periodically enter the solar system, causing disruptions and changes to the local cosmic landscape? If this was the case, it would mean that 3I Atlas was just one of many such visitors that have passed through our solar system over the eons, potentially altering the orbits of planets, moons, and asteroids. The idea that our solar system is not isolated, but rather connected to the broader galactic environment, challenges our traditional understanding of cosmic stability. The arrival of 3I Atlas and its companions raises important questions about the forces at play in interstellar space, and what it means for the future of our solar system. As astronomers continue to study 3I Atlas and its companions, they are not only uncovering the mysteries of these objects, but also expanding our understanding of the dynamics of the galaxy itself. As 3I Atlas made its way through the solar system, astronomers were astounded by the sudden appearance of a growing number of objects, each with its own unique story and trajectory. These weren't the usual stray asteroids or comets that would pass by every now and then following their long-established orbits. These objects seemed to be part of a much larger, more coordinated cosmic event, an influx of material arriving in a short window of time, as though some unseen cosmic force had orchestrated the entire spectacle. The most immediate question that arose from this sudden surge was whether there was a connection between the new arrivals and the interstellar object 3I Atlas. Could these objects, which included asteroids, comets, and other cosmic wanderers, have been influenced or even drawn to the solar system by 3I Atlas itself? Was this a simple coincidence, or was there a deeper, more profound mechanism at work? Some of the most notable arrivals in this cosmic swarm were comets, mysterious icy visitors from the far reaches of space. Comet C/2025 R2, which had been discovered earlier in the year, quickly gained attention. This comet, which was already brightening towards naked-eye visibility, had begun its journey across the solar system with a spectacular tail that grew longer with every passing day. Astronomers couldn't help but notice the timing of its approach. Discovered just weeks before 3I Atlas, its trajectory appeared to coincide perfectly with the interstellar object's approach to the Sun. In addition to this comet, a series of asteroids also entered the solar system during the same period, some of them coming remarkably close to Earth. These objects, like the comets, seemed to appear out of nowhere, and their presence could not be easily dismissed as just random occurrences. The sheer number of objects arriving in this narrow window of time raised suspicions. Were they all simply coincidental, or was something about 3I Atlas triggering their arrival? As astronomers carefully studied the orbits and trajectories of these objects, it became increasingly clear that they were not all following their expected paths.
Some seemed to be slightly altered, as though their trajectories had been influenced by an external force. Could 3I Atlas, with its unusual velocity and trajectory, be causing some kind of gravitational disturbance that was affecting the orbits of nearby objects? Could its passage through the solar system be pulling or pushing these objects into new paths, guiding them toward Earth and the other planets? These questions began to gain traction as more and more objects were identified in the path of 3I Atlas. But there was one key question that lingered above all others. Why was this happening now? Was it simply a rare cosmic event, or could the arrival of 3I Atlas be a sign of something larger and more significant occurring within the solar system?
One of the most intriguing hypotheses that arise from the unexpected surge in cosmic objects was the possibility that 3I Atlas itself was responsible for altering the paths of nearby objects. While objects in the solar system generally follow stable orbits dictated by the Sun's gravity, the arrival of an interstellar object like 3I Atlas was far more unpredictable. Its velocity, trajectory, and interaction with the solar system's gravitational field were unlike anything that had been seen before. Could such a high-speed, hyperbolic object actually be exerting gravitational influence on other bodies in the solar system? The answer, as it turned out, wasn't as straightforward as one might think. In celestial mechanics, gravity is a fundamental force that governs the motion of all objects in space. The more massive an object is, the stronger its gravitational pull. The Sun, as the largest object in the solar system, exerts the most powerful gravitational influence, which keeps the planets, asteroids, and comets in their respective orbits. However, even smaller objects can have an impact on nearby bodies, especially when they are moving at high speeds. Astronomers began to consider the possibility that 3I Atlas's hyperbolic trajectory might be disrupting the orbits of nearby objects, causing them to change course. The gravitational influence of 3I Atlas might not be enough to dramatically alter the orbits of the planets, but could it be affecting the smaller, more fragile objects that make up the solar system's small body population? The answer, it seemed, was yes, at least to some extent. The gravitational pull of 3I Atlas could be causing subtle shifts in the trajectories of objects in the asteroid belt or the Oort cloud. Even a small gravitational influence could be enough to nudge a comet or asteroid into a new path, especially when the object was moving as quickly as 3I Atlas. Over the course of millions or even billions of years, such shifts could result in significant changes in the orbits of these objects, guiding them into the inner solar system where they could potentially collide with planets or other celestial bodies. Astronomers also began to consider the possibility that 3I Atlas's gravitational influence might be interacting with the solar wind and magnetic fields within the solar system. This complex interaction between gravitational forces and electromagnetic forces could be creating a feedback loop that draws other objects into the solar system or alters their trajectories in unexpected ways. In addition to the gravitational influence that 3I Atlas might be exerting on nearby objects, scientists began to speculate about another possibility. Could electromagnetic forces be at play? Interstellar objects, especially those traveling at the high speeds of 3I Atlas, are subject to a wide range of cosmic forces, including electromagnetic fields, solar radiation, and cosmic rays. These forces could be interacting with the material making up 3I Atlas in ways that were not fully understood. Electromagnetic forces are responsible for many phenomena in space, including the behavior of comet tails and the interactions between charged particles in the solar wind. As 3I Atlas approaches the Sun, it will begin to experience increasing levels of solar radiation, which can cause the object to release gas and dust, forming a coma and tail. This process, known as sublimation, is what makes comets visible from Earth, as the outgassing creates the characteristic bright tail that points away from the Sun. 3I Atlas is no ordinary comet. The object's composition, chemical makeup, and high velocity suggest that it might be subject to more complex electromagnetic interactions than typical comets. Some scientists proposed that 3I Atlas's electromagnetic field might be influencing nearby objects in the solar system, causing them to shift their trajectories or accelerate toward the inner solar system. If this hypothesis is correct, it would mean that 3I Atlas is not only exerting a gravitational influence on nearby objects, but also triggering electromagnetic forces that further alter the behavior of these objects. This would add another layer of complexity to the already puzzling surge of cosmic arrivals. As 3I Atlas and its companions made their way through the solar system, the role of the Sun became increasingly important in understanding the behavior of these objects. The Sun's influence on the solar system is well established. It is the source of light, heat, and gravitational pull that keeps the planets in orbit. However, the Sun also has a more subtle but equally significant effect on smaller objects in the solar system. The solar wind, a stream of charged particles emitted by the Sun, interacts with comets and asteroids in various ways. As 3I Atlas approaches the Sun, the solar wind begins to push against the object's coma, causing the tail to stretch and shape. The strength and direction of the solar wind can also affect the trajectories of comets and asteroids, especially those with weak gravitational binding forces. For 3I Atlas, the solar wind will play a crucial role in shaping its behavior as it passes through the solar system. The object's tail, which is composed of gas and dust, will interact with the solar wind in ways that might create a feedback loop, altering the object's path or triggering new bursts of activity. If 3I Atlas is exerting any influence on nearby objects, the Sun's electromagnetic forces could amplify or modulate this effect, making the interactions even more complicated. The solar wind is not just a passive force, it actively shapes the behavior of objects in the solar system. As 3I Atlas and its companions move through the solar system, the strength and intensity of the solar wind could play a key role in their trajectories and interactions, potentially providing a link between the surge of cosmic arrivals and the arrival of 3I Atlas itself. As astronomers continue to study the influx of objects arriving with 3I Atlas, they are uncovering new insights into the dynamics of the solar system. These unexpected arrivals challenge our understanding of the solar system's structure and behavior. If 3I Atlas and its companions are indeed interacting with the solar system, it could lead to breakthroughs in our understanding of how objects from outside the solar system influence the inner workings of our cosmic neighborhood. By studying the trajectories of these objects, astronomers can learn more about the gravitational forces at play in the solar system, as well as the role of electromagnetic interactions in shaping the behavior of comets and asteroids. These observations will help refine models of planetary defense, improving our ability to track and understand the behavior of objects that might pose a threat to Earth in the future. Furthermore, the study of 3I Atlas and its companions offers a rare opportunity to learn about the composition and behavior of objects from other star systems. As these objects pass through the solar system, they provide a snapshot of the conditions and processes that govern the formation of planets and stars beyond our own solar system. These cosmic visitors are not just passing through, they are helping us expand our understanding of the universe, one object at a time. The universe, as vast as it is, often seems chaotic and random. Yet within that chaos, there are moments when the odds of certain events occurring seem so slim that one cannot help but question whether these occurrences are purely coincidental or part of something larger. The appearance of 7 comets, each with its own origin, trajectory, and path toward the Sun, all arriving in the same window of time, within mere months of each other, is one of those events. Astronomers are no strangers to the unpredictable nature of the cosmos. They expect the occasional comet to pass through the solar system, usually as isolated objects with well-understood orbits. But a swarm of 7 comets, each with its own specific timing, trajectory, and characteristics, all appearing within the same few months? This is a rarity so extraordinary that it seems almost too unlikely to be random. For decades, astronomers have studied the paths of comets and asteroids with the assumption that their arrivals follow the natural order dictated by gravitational mechanics. However, when an event like the 2025 comet surge occurs, an influx of 7 comets converging in such a short time frame, it challenges the traditional understanding of cosmic randomness. The 7 comets that appeared in 2025, all of which were tracked by astronomers around the world, seemed to follow distinct paths, yet their convergence in space and time was anything but typical. Some came from the Oort cloud, the vast region of icy bodies at the outermost reaches of the solar system, while others originated from different areas within the solar system. Their arrival during the same period raised questions. How could such a coincidence occur? Could there be an underlying connection, some unseen force guiding their paths toward the Sun at the same time? The appearance of these 7 comets, most notably Comet C/2025 R2, Comet Pan-STARRS, and Comet Atlas K1, set astronomers on edge, sparking discussions about the patterns that might exist in the cosmos. Could the presence of one interstellar object, 3I Atlas, be connected to the arrival of these other cosmic travelers? What is the likelihood that 7 comets, each with its own distinct trajectory and origin, could appear at the same time in a solar system that has, for millions of years, followed relatively predictable patterns?
The statistical odds of such an event are staggering. Normally, the arrival of a single comet or asteroid is a rare event. Comets that come close to Earth or the Sun are often on long elliptical orbits that take them far beyond the outer planets for most of their journey. Yet in 2025, this pattern was disrupted in a way that was impossible to ignore. The convergence of these 7 comets within such a small time window was a fluke so improbable that it sparked a wave of speculation. Were these comets following their own regular orbits, or was something else influencing their arrival? Some scientists proposed that a gravitational anomaly, perhaps related to the solar system's movement through space, could be responsible. Others speculated that the presence of 3I Atlas might be causing a shift in the gravitational field of the solar system, leading to the altered paths of these comets. The timing and nature of these arrivals seemed to defy the conventional understanding of how comets and other objects enter our solar system. As the astronomical community scrambled to understand the true nature of this cosmic event, the question remained: was this rare clustering of comets simply an incredible stroke of luck, or was there a deeper, more significant force at play? The statistical improbability of 7 comets arriving in such close proximity to one another seemed at first to be a mere coincidence. But as more data came in, scientists began to wonder if there could be a connection between these objects and the arrival of 3I Atlas. If the arrival of 7 comets wasn't a coincidence, then what could explain their timing? Could 3I Atlas, with its interstellar origins and high-speed trajectory, be influencing the solar system in ways that had never been observed before?
The object was traveling at an incredible velocity, far faster than anything seen in the solar system, and its hyperbolic orbit indicated that it was simply passing through the solar system rather than becoming gravitationally bound to it. However, its high speed and approach from a completely different direction raised questions about its potential impact. The most obvious explanation that came to mind was the possibility of gravitational interaction. Gravitational forces are incredibly powerful, and even a small object moving at high speeds can have a significant effect on the trajectories of nearby bodies. Could 3I Atlas, with its enormous velocity and unusual path, be causing subtle shifts in the orbits of nearby comets, asteroids, and other objects? The gravitational pull of 3I Atlas, though weaker than that of more massive objects like the Sun or Jupiter, could still be enough to nudge nearby comets into slightly altered trajectories. This kind of gravitational interaction is known to occur in the solar system regularly, especially when comets pass close to the giant planets. However, the arrival of 7 comets in such a short period was unprecedented, and astronomers wondered whether 3I Atlas was the catalyst for these events.
As the scientific community pondered this question, another possibility began to emerge. Could electromagnetic forces be at play? In addition to gravitational influence, objects in space are subject to a variety of electromagnetic forces, such as the solar wind and cosmic radiation. These forces can interact with comets and asteroids, affecting their tails and overall behavior. Could 3I Atlas, with its unusual composition and high velocity, be generating electromagnetic waves that are affecting nearby objects, drawing them toward the solar system? Though this theory was speculative, it opened up new avenues for research. The possibility that 3I Atlas's electromagnetic field could be influencing other objects in the solar system challenged the conventional understanding of how comets behave. It suggested that there might be more to these cosmic visitors than just their gravitational interactions with the Sun. Instead, they might be part of a larger cosmic dance, influenced by forces that scientists had yet to fully understand. As scientists continued to debate the role of 3I Atlas in the appearance of the 7 comets, it became clear that the object's influence on the solar system was not purely gravitational. The presence of electromagnetic forces, generated by the high-speed object and its unusual composition, might also be playing a role in altering the behavior of nearby comets and asteroids. One of the key factors in understanding this influence was the object's high velocity. 3I Atlas was moving at speeds far exceeding those of typical solar system objects, which meant that its gravitational field would be weaker, but its speed would generate powerful electromagnetic effects. As the object neared the Sun, the solar wind would interact with 3I Atlas's coma and tail, generating magnetic fields that could, in turn, affect nearby objects in space. Could this magnetic interaction be causing comets to change course, accelerating their arrival into the inner solar system? In addition to these electromagnetic effects, the chemical composition of 3I Atlas also played a role in its influence on the surrounding space. The object's unique chemical signatures, such as the high levels of carbon dioxide and cyanogen, might be interacting with the solar wind in ways that were not yet fully understood. Could these chemical anomalies be affecting the behavior of nearby objects, either by altering their physical properties or by interacting with their magnetic fields? To better understand these forces, astronomers began analyzing the object more closely, using a combination of observational data and theoretical models. These models sought to explain how 3I Atlas's high velocity, unusual composition, and electromagnetic interactions could be influencing nearby comets and asteroids. What they found was both surprising and puzzling. The influence of 3I Atlas appeared to extend much farther than expected, potentially affecting objects far beyond the immediate vicinity of the interstellar visitor itself. As astronomers dug deeper into the data, a new theory began to take shape. Could 3I Atlas be acting as a cosmic trigger, initiating the appearance of these other objects in the solar system? Rather than being a passive participant in the cosmic event, 3I Atlas might be actively interacting with the solar system's small body population, influencing their trajectories and bringing them into the inner solar system. This theory suggested that 3I Atlas, in combination with its gravitational and electromagnetic influence, might be causing a chain reaction among nearby objects, triggering their arrival and altering their orbits. It was as if 3I Atlas had set off a cosmic ripple effect, causing a series of comets and asteroids to move toward the Sun, as though they were being pulled into its orbit. The idea that 3I Atlas might be acting as a trigger raised further questions. Could this be a natural phenomenon that occurs regularly, or was this a once-in-a-lifetime event? If 3I Atlas's influence on nearby objects could trigger their arrival, what other objects might be affected in the future? Would we see similar influxes of objects in the years to come, each triggered by interstellar visitors passing through the solar system? This idea also raised questions about the stability of the solar system itself. If 3I Atlas's passage could have such a profound effect on the orbits of objects in the Oort cloud or the asteroid belt, what other forces were at play in the broader cosmic environment? The idea of an interstellar object acting as a catalyst for changes in the solar system challenged the conventional understanding of gravitational mechanics and planetary dynamics. It suggested that the solar system might be more interconnected with the rest of the galaxy than previously thought. As the surge of cosmic arrivals continued, astronomers began to realize that these events were more than just curiosities, they were opportunities for discovery. The interactions between 3I Atlas and the other objects in the solar system were providing a wealth of new data about the forces that shape the universe. These objects were not simply passing through, they were offering glimpses into the larger dynamics of the solar system and beyond. By studying the trajectories and chemical compositions of these objects, scientists could gain new insights into the processes that govern the formation of planets and stars. They could learn more about the behavior of interstellar objects as they pass through our solar system, and about the interactions between gravitational forces, electromagnetic fields, and cosmic radiation. This new understanding of cosmic dynamics would also be crucial for planetary defense. As the study of 3I Atlas and its companions continued, it became clear that monitoring interstellar visitors and their effects on the solar system would be essential for understanding potential threats to Earth in the future. The study of 3I Atlas was not just about curiosity. It was about ensuring that humanity was prepared for whatever cosmic challenges lay ahead. The appearance of 3I Atlas in our solar system, accompanied by the sudden surge of comets and asteroids, challenged the traditional view of the solar system as a relatively stable and predictable system. In the past, astronomers could rely on the laws of gravity and orbital
mechanics to predict the arrival of comets and asteroids with a high degree of certainty. Yet the timing of 3I Atlas's passage and the simultaneous arrival of several other objects from different regions of space created an anomaly that was difficult to explain. In the years to come, scientists might look back at this event as a rare, isolated incident. But the more they studied it, the more they began to wonder if it was part of a much larger, cyclical pattern, a natural rhythm of cosmic events that humanity had simply not yet recognized. Could 3I Atlas, with its high-speed approach and interstellar origins, be part of a broader cosmic pattern of objects periodically passing through the solar system? And if so, how often could such events occur? One of the most intriguing possibilities that began to take shape was the idea that 3I Atlas was not a singular anomaly, but rather a herald of future interstellar visitors. As astronomers began to analyze its orbit and trajectory, they realized that such objects,
Comets, asteroids, or even small planets could be on long elliptical orbits that would bring them back to the solar system after thousands or even millions of years. Could the solar system be periodically visited by objects from other stars, each carrying new information about the galaxy? The gravitational influence of 3I Atlas might have been just one part of a much larger galactic cycle. With its passage, it could have created ripples in the cosmic fabric, nudging other objects in the process. In a way, 3I Atlas might have been the beginning of a chain reaction, a cosmic event that had been set in motion long before our solar system formed. As this idea gained traction, astronomers began to shift their focus. Instead of merely considering 3I Atlas as a random visitor, they started asking whether it was part of an ongoing cosmic rhythm. What if the solar system was simply one stop in the journey of interstellar objects, traveling through space in a pattern that was far older and more intricate than previously imagined? Could our solar system, isolated as it may seem, be more connected to the greater galactic landscape than we've ever thought possible? The study of 3I Atlas, along with the other objects that appeared during its passage, raised important questions about the solar system's place in the galaxy. In many ways, the solar system has always been viewed as a relatively isolated system, with the Sun at the center and the planets, moons, and comets moving in predictable orbits. However, the arrival of 3I Atlas challenged this notion, suggesting that our solar system might not be as isolated as we once thought. The discovery of 3I Atlas was a reminder that interstellar space is full of objects that could one day make their way into our solar system. These objects, which have traveled across vast distances from other star systems, bring with them a unique opportunity to study the conditions of planetary formation and the properties of distant stellar environments. For the first time, scientists had the chance to observe an object that had never been bound by the gravitational forces of the Sun, allowing them to learn about the physics of objects that come from outside our solar system. In the case of 3I Atlas, scientists were particularly interested in its chemical composition, which was unlike anything seen in our local solar system. Observations made by the James Webb Space Telescope and other instruments revealed the high presence of carbon dioxide and cyanogen in the comet's coma. These compounds were far more prevalent than the water vapor and methane typically found in comets from the Oort cloud. The unique mixture of chemicals in 3I Atlas raised fascinating questions about its formation, its journey across the galaxy, and the conditions of the stellar system from which it came. The presence of such materials in 3I Atlas suggested that objects from other star systems might have very different chemical compositions than those found in our own solar system. Could this mean that other star systems, particularly those with different temperatures, pressures, and planetary compositions, have a far wider range of chemical possibilities than we have observed in our own solar neighborhood? Studying 3I Atlas could give scientists critical insights into the diversity of planets, stars, and the chemistry of the galaxy at large. Moreover, 3I Atlas wasn't just a visitor. It was a piece of the puzzle that could help explain how stars form, how planetary systems evolve, and even how life might develop in other parts of the galaxy. The chemical and physical characteristics of 3I Atlas, as well as the conditions that allowed it to travel across interstellar space for billions of years, could provide clues to understanding the broader processes that govern the formation of stars and planets. By studying these interstellar objects, we might one day be able to learn more about how life, as we know it, might exist on planets far outside our solar system. While the scientific community eagerly embraced the new knowledge brought by interstellar objects like 3I Atlas, another important question began to emerge. Could these visitors pose a threat to our solar system, particularly to Earth? The surge of objects that arrived along with 3I Atlas had sparked a renewed sense of urgency in the field of planetary defense. For many years, astronomers have tracked near-Earth objects, NEOs, that could potentially collide with our planet. And 3I Atlas raised questions about how much we truly understood about objects that are not native to our solar system. The possibility of a collision with a massive interstellar object or a comet arriving on a trajectory that had been altered by 3I Atlas could have devastating consequences for Earth. While 3I Atlas was not on a collision course with our planet, the event raised the issue of preparedness. If more interstellar objects were to follow a similar path, what could humanity do to protect itself? As astronomers tracked the trajectory of 3I Atlas and its companions, it became clear that the current planetary defense systems were not equipped to deal with objects that arrive from outside our solar system. These interstellar visitors do not follow the same patterns as objects that have been bound by the sun, and their paths are harder to predict. The sudden
appearance of a fast-moving object, like 3I Atlas, would not give Earth's defense systems enough time to mount an effective response. This realization led to a broader discussion about planetary defense in the 21st century. Currently, the global effort to track and monitor near-Earth objects relies on telescopes that scan the skies for potential threats. These telescopes are designed to spot objects that are within the solar system, particularly those that could come dangerously close to Earth. However, detecting interstellar objects like 3I Atlas is far more challenging. Unlike comets and asteroids that are bound to the sun, interstellar objects can approach from any direction and can travel at much higher velocities. They are not subject to the same gravitational influences, which makes them harder to track. As scientists begin to realize the vulnerability of Earth to interstellar threats, the need for a more robust planetary defense system becomes apparent. In the future, humanity will need to develop better detection systems that can identify interstellar objects earlier in their approach. Advanced space-based observatories, as well as the ability to track objects beyond the solar system, will be essential for ensuring that Earth is prepared for any potential threat. While 3I Atlas was the first confirmed interstellar object to visit the solar system in decades, scientists began to wonder whether it would be the last. Could 3I Atlas be just the beginning of a new era of interstellar exploration? Could the solar system, once thought to be isolated, actually be a frequent destination for interstellar objects? The possibility of more interstellar objects entering the solar system in the future raised important questions about the dynamics of these objects and their potential impact on the solar system. 3I Atlas's high velocity and trajectory suggested that it was just passing through. But what if future objects followed similar paths, arriving with little warning and altering the dynamics of the solar system? The fact that 3I Atlas arrived so unexpectedly had sparked a new sense of urgency in the astronomical community. Could the solar system be part of a much larger interstellar network, with objects periodically traveling through the system over the course of millions of years? The more scientists studied 3I Atlas, the more they began to suspect that it was part of a broader galactic process. In the future, the solar system could be visited by more interstellar objects, each carrying with it a wealth of information about the broader universe. As technology improves, astronomers might be able to detect these visitors long before they reach the solar system, allowing us to prepare for their arrival and learn from their presence. The study of 3I Atlas and other interstellar objects also prompted a larger conversation about humanity's place in the galaxy. If our solar system is a regular stop for interstellar visitors, what does that say about the broader nature of space travel? Are there other civilizations out there in the galaxy, traveling across vast distances to explore new star systems, just as 3I Atlas had? The arrival of these cosmic wanderers opened up new possibilities for understanding the universe and our role in it. Looking forward, the study of 3I Atlas and the surge of cosmic arrivals it brought with it will play a crucial role in shaping the future of planetary defense and space exploration.
As astronomers continue to observe the paths of interstellar objects and refine our ability to track and predict their movements, new technologies will be developed to better protect Earth from potential threats. The events of 2025, sparked by the appearance of 3I Atlas, will likely serve as a catalyst for global cooperation in space science. Nations around the world will need to work together to develop more advanced detection systems, as well as defense mechanisms that can be deployed if an interstellar object poses a risk to Earth. Moreover, the study of these objects will undoubtedly lead to exciting new discoveries about the nature of the universe. By observing the chemical compositions and trajectories of interstellar visitors, scientists will be able to learn more about the formation of stars and planets in other parts of the galaxy. These discoveries could help us understand the origins of our own solar system and offer clues about the potential for life elsewhere in the universe. As humanity continues its journey into space, the lessons learned from studying 3I Atlas and its companions will serve as a reminder that our solar system is not an isolated island, but rather part of a much larger cosmic community, one that is full of surprises, mysteries, and untold stories waiting to be discovered. The arrival of 3I Atlas in the solar system sparked significant interest in the concept of interstellar objects. These visitors from other star systems had only recently become a major subject of study, and 3I Atlas, with its peculiar speed and trajectory, was a prime candidate for further investigation. However, one question loomed large. How far do these objects travel before reaching our solar system? And what is their journey like? Interstellar objects, by definition, come from outside the solar system. This means they are not bound by the sun's gravitational influence, as are comets or asteroids that exist in our solar system. Instead, they are free-roaming wanderers that travel across vast stretches of space, often for millions or even billions of years, before entering our solar system. The vast distances these objects travel are mind-boggling. For instance, 3I Atlas likely originated from a star system located hundreds of light-years away from Earth. It has traveled across interstellar space, a region of space between the stars that is nearly empty, save for a sparse scattering of dust, gas, and cosmic radiation. The journey from its home star system to ours likely took millions of years, as it moved through the quiet, vast stretches of space at high velocity. Upon entering our solar system, it had already covered an incomprehensibly long distance, making its brief passage through the solar system all the more remarkable.
The sheer scale of these journeys raises fascinating questions about the nature of our galaxy. 3I Atlas's passage reminded us that the universe is not static, but rather filled with objects that are constantly on the move. These objects are the travelers of the cosmos, carrying with them information about the stars, the planets, and the conditions of distant galaxies. The study of these objects provides a unique opportunity to look beyond our solar system and gain insights into the broader workings of the galaxy. What makes interstellar objects like 3I Atlas so intriguing is that they offer a snapshot of a different stellar environment. They are time capsules holding clues to the formation of stars, planets, and even the possibility of life in other parts of the galaxy. As 3I Atlas made its way through the solar system, astronomers had the rare opportunity to study an object that had traveled across space for millions of years, carrying with it a history of a distant star system. Astronomers are keenly aware that 3I Atlas is just one of many interstellar objects that may eventually pass through the solar system. With advances in technology and improved telescopic surveys, scientists are now able to identify these objects earlier in their journey, giving them the opportunity to study them in greater detail. The arrival of 3I Atlas is a reminder that our solar system is not isolated. It is part of a dynamic, interconnected universe where objects from other star systems are constantly moving through space, waiting to be discovered.
Understanding how objects like 3I Atlas enter our solar system is key to unraveling the mystery of their journey. Unlike comets and asteroids that are gravitationally bound to the Sun and follow predictable orbits, interstellar objects travel through space on trajectories that are not influenced by the Sun's gravity. This means they can approach the solar system from any direction and at any speed, making their arrival difficult to predict. Interstellar objects typically approach the solar system from the outer reaches of space, entering the Oort cloud, the vast icy shell of objects that surrounds the solar system at a distance of over 50,000 astronomical units. Once they pass through this region, they begin to feel the Sun's gravitational influence, which can alter their trajectory and pull them toward the inner solar system. However, the Sun's gravity is not strong enough to capture these objects into long-term orbits. Instead, they follow hyperbolic trajectories, meaning they are destined to continue their journey through the solar system and out into interstellar space once again. The trajectory of 3I Atlas, for instance, was a hyperbolic orbit that took it past the Sun and out of the solar system. As it approached the Sun, it accelerated due to the gravitational pull of the star, but it didn't slow down enough to become bound by the Sun's gravity. Instead, 3I Atlas sped past the Sun, continuing on its path toward the outer reaches of the galaxy. This kind of high-speed passage is typical of interstellar objects, as their velocities are far greater than those of objects that are gravitationally bound to the solar system. What makes these objects particularly interesting to scientists is that they don't follow the same laws of motion as the rest of the solar system. Their trajectories and velocities are influenced by factors that we are still trying to understand. The passage of interstellar objects like 3I Atlas offers a unique opportunity to study the forces at work in the broader galaxy, forces that operate on much larger scales than those we observe in our own solar system. As 3I Atlas passed through the solar system, it was not just a celestial wanderer. It was a messenger from another star system. Its high velocity and unusual trajectory allowed scientists to observe its behavior and composition in ways that were not possible for objects that have been part of the solar system for eons. By studying the movement and characteristics of these objects, astronomers can learn more about the dynamics of interstellar space and the broader processes that govern the formation of stars and planets. As 3I Atlas and other interstellar objects pass through the solar system, one of the most important forces at play is the Sun. The Sun's gravity has a significant impact on the trajectories of objects that enter the solar system, especially those that are moving at high velocities like 3I Atlas. When these objects approach the Sun, they begin to accelerate due to the Sun's gravitational pull, causing them to increase in speed. However, the Sun's gravitational influence is not always enough to capture these objects into orbit. Instead, they are often deflected, continuing on their way through the solar system and out again. This deflection process is one of the most fascinating aspects of the Sun's interaction with interstellar objects. The Sun's gravity is strong enough to alter the trajectory of an object, but not strong enough to hold it within the solar system indefinitely. The result is a high-speed passage that carries the object through the inner solar system, potentially passing by the planets and other bodies before speeding off into interstellar space once more. For astronomers, this provides a unique opportunity to study the Sun's gravitational influence on objects that are not bound to the solar system. Interstellar objects like 3I Atlas pass through the Sun's gravitational field at high velocities, which can reveal insights into the dynamics of the solar system's gravitational environment. By studying how these objects are deflected and how their paths change as they approach the Sun, scientists can learn more about the solar system's gravitational structure and how it interacts with objects from other star systems. One of the key factors in understanding the Sun's influence on interstellar objects is the speed at which they travel. 3I Atlas, for example, was moving so quickly that its encounter with the Sun was brief, and its velocity meant that it would not be captured by the Sun's gravity. Instead, the object passed by the Sun in a high-speed encounter, continuing its journey into the depths of space. This kind of high-speed passage is typical of interstellar objects, and it highlights the difference between objects that are gravitationally bound to the solar system and those that are simply passing through. One of the most exciting aspects of studying interstellar objects like 3I Atlas is the unique opportunity they provide to examine the chemical makeup of other star systems. These objects carry with them a wealth of information about the conditions in the star systems they originated from, information that can shed light on the processes that govern the formation of stars, planets, and even life in other parts of the galaxy.
In the case of 3I Atlas, its chemical composition was unlike anything seen in objects that originate within the solar system. Observations made by telescopes such as the James Webb Space Telescope revealed the presence of unusual compounds, including high levels of carbon dioxide and cyanogen. These compounds are rarely found in comets from the Oort cloud, and their presence in 3I Atlas suggested that the object originated in a very different environment, one with conditions that were far colder and chemically distinct from the solar system's outer regions. The chemical composition of 3I Atlas provides valuable insights into the formation of planetary systems in other star systems. By studying the chemicals present in interstellar objects, scientists can learn more about the types of materials that exist in other parts of the galaxy. These materials, which are often vastly different from the compounds found in the solar system, could offer clues about how planets form in other star systems and what conditions might be necessary for life to emerge. The presence of cyanogen, a highly toxic chemical compound, in 3I Atlas is of particular interest to scientists. Cyanogen is made up of carbon and nitrogen, two of the building blocks of life. Its presence in 3I Atlas suggests that there may be more similarities between interstellar objects and the basic components of life than previously thought. It raises the question of whether the ingredients for life are more common in the galaxy than we've realized. In addition to revealing information about the conditions in other star systems, the study of interstellar objects like 3I Atlas also has profound implications for our understanding of the origins of our own solar system. The chemical materials found in these objects could help us piece together the history of our own planet and the forces that shaped its formation. The arrival of 3I Atlas and its companions marks a pivotal moment in our understanding of the solar system and our place in the galaxy. These interstellar visitors are not just passing curiosities, they offer a glimpse into the broader dynamics of space and the forces that govern the behavior of objects across the galaxy. The study of 3I Atlas and other interstellar objects provides valuable information about the formation and evolution of planetary systems, as well as the broader processes that govern the behavior of celestial bodies. By studying these objects, astronomers can learn more about the conditions that exist in other star systems and how they compare to our own. They can also gain insights into the forces at work in the wider universe, including the effects of interstellar dust, cosmic radiation, and gravitational influences. These interstellar visitors remind us that the solar system is not isolated, but rather part of a much larger, interconnected galaxy. As 3I Atlas and other objects pass through the solar system, they provide new data that can help scientists refine their models of galactic dynamics. In the future, we may come to understand that the solar system is regularly visited by interstellar objects, each carrying new information about the galaxy and the universe beyond. By studying these visitors, we are not only learning about the history of the solar system, but also about the future.
The study of 3I Atlas and its companions offers a unique opportunity to expand our understanding of the universe and our place within it. While the passage of 3I Atlas was certainly a rare event, it has opened up a significant conversation about planetary defense in the future. As the scientific community processed the information surrounding the arrival of this interstellar visitor, one clear implication began to emerge. Earth is not as isolated as we once believed. The presence of 3I Atlas and its ability to enter our solar system with little to no warning has prompted experts to reconsider how we track and prepare for interstellar objects in the future. Planetary defense has long focused on monitoring near-Earth objects, NEOs, asteroids and comets that travel in orbits close to the Earth. While much of this work has been dedicated to preventing asteroid impacts, the discovery of interstellar objects like 3I Atlas has highlighted a new vulnerability. Objects arriving from outside the solar system, moving at incredibly high speeds and on unpredictable trajectories. These objects are not gravitationally bound to our Sun, making them much more difficult to track and predict than their solar system counterparts. Unlike the regular monitoring of NEOs, interstellar objects could arrive from any direction without the same patterns or gravitational relationships that govern other celestial bodies. The high speed and velocity of interstellar objects also make them far more challenging to intercept or redirect should they pose a risk to Earth. The arrival of 3I Atlas has made it clear that Earth needs to expand its planetary defense capabilities to include tracking interstellar objects, as well as developing strategies for responding to objects that come from outside the solar system. The most obvious question that arises is, how can we track these objects more effectively? As 3I Atlas's passage demonstrated, existing telescopic surveys are geared toward detecting objects already within the solar system, not ones coming from outside. There is an urgent need for telescopes and other space-based instruments that are designed to track objects at greater distances, scanning the edges of the solar system and beyond. Improved detection methods could allow scientists to spot interstellar objects much earlier, giving us more time to study their trajectories and assess any potential risks. Moreover, the challenge extends beyond detection to the actual mitigation of any potential threats posed by interstellar objects. While 3I Atlas did not pose a direct threat to Earth, a future object on a collision course could have catastrophic consequences. The high speed and unpredictable nature of interstellar objects would make it incredibly difficult to intercept or redirect them. Planetary defense strategies will need to evolve to consider the possibility of such high-velocity objects, including technologies capable of altering their paths or safely diverting them. One possible avenue for this type of defense might involve advanced propulsion systems or kinetic energy weapons that could be used to intercept or deflect objects before they can reach Earth. However, such technologies are still in their infancy, and the task of developing them for practical use is a monumental challenge. Nevertheless, the passage of 3I Atlas has
underscored the importance of investing in planetary defense, ensuring that Earth is prepared for potential future encounters with objects from beyond our solar system. The study of 3I Atlas and other interstellar objects has highlighted the need for advanced observational tools to better understand the behavior of these objects and track their movements as they pass through the solar system. Current telescopic surveys primarily focus on objects that are within the solar system's gravitational influence. However, to detect and study interstellar visitors, new technologies must be developed that can observe objects coming from outside the solar system. One of the key challenges in tracking interstellar objects is their speed. Unlike comets and asteroids that orbit the Sun and have relatively predictable velocities, interstellar objects are traveling much faster, often at speeds that exceed the escape velocity of the solar system.
For example, 3I Atlas was moving at speeds that were orders of magnitude higher than typical objects within the solar system. This high velocity makes it difficult for conventional telescopes to track these objects, especially if they are approaching from an unfamiliar direction. In the case of 3I Atlas, the object was detected only after it had already entered the inner solar system, with its trajectory and speed already determined. This late detection left little time for detailed observation or research before the object passed through the solar system and began its journey back into interstellar space. With the increasing likelihood of future interstellar visitors, astronomers are working to develop more advanced telescopic systems that can detect objects like 3I Atlas at much greater distances, providing ample time for study and analysis. One solution to this challenge might involve building space-based observatories that can monitor deep space beyond the solar system's boundaries. These observatories would be capable of spotting objects long before they enter the solar system, providing astronomers with valuable data on their trajectory and chemical composition. In addition, space-based instruments could be better equipped to track high-speed objects without the interference of Earth's atmosphere, which often distorts observations made from ground-based telescopes. Another key development would be the use of artificial intelligence, AI, and machine learning algorithms to process the massive amounts of data gathered by these observatories. AI could be trained to detect objects that are on trajectories toward the solar system, analyzing vast swaths of sky data and identifying potential interstellar visitors far earlier than current systems allow. With AI, astronomers could predict the paths of these objects with a much higher degree of precision, enabling the scientific community to prepare for their arrival and plan for any necessary response. As these technologies continue to advance, the ability to detect and study interstellar objects will become more refined, giving scientists greater insight into the nature of the universe and the broader forces that govern the movements of cosmic bodies. The passage of 3I Atlas through our solar system offered an unprecedented opportunity for scientific discovery. Interstellar objects, by virtue of their origin, carry with them a wealth of information about the conditions of distant star systems. While much of the focus on planetary defense and tracking these objects is understandably on the potential risks they pose, it is important to recognize the tremendous scientific value that comes with studying these visitors. Interstellar objects like 3I Atlas are time capsules containing chemical and physical information that can tell us a great deal about the star systems from which they originated. These objects are not bound by the same forces that govern our solar system, and they have not undergone the same processes of formation and evolution as objects in our own stellar neighborhood. As a result, studying their chemical composition, structure, and behavior provides a unique glimpse into the conditions of other star systems and the broader dynamics of the galaxy. The chemical makeup of 3I Atlas, in particular, was of immense interest to scientists. Observations of the object revealed the presence of compounds that were not typically found in comets from our solar system, such as cyanogen and carbon dioxide. These chemicals, while not inherently dangerous, were fascinating to scientists because they suggest that 3I Atlas came from a star system with different environmental conditions from our own. The presence of these compounds could reveal details about the formation of planets, the types of materials available in the object's original environment, and the processes that shaped its journey across the galaxy. In addition to its chemical composition, 3I Atlas also offered astronomers the chance to study its movement through the solar system. Its high velocity and hyperbolic trajectory presented a rare opportunity to understand the forces that govern the motion of objects traveling through interstellar space. By tracking the object's path, scientists could learn more about the gravitational and electromagnetic forces at play as it passed through the solar system. As astronomers continue to study interstellar objects like 3I Atlas, they hope to uncover new insights into the processes of star and planet formation, as well as the broader dynamics of the galaxy. The study of these objects could one day lead to breakthroughs in our understanding of the origins of our own solar system, as well as the potential for life in other parts of the universe. The study of interstellar objects like 3I Atlas also has profound implications for the future of space exploration. As humanity ventures further into the cosmos, the knowledge gained from studying these visitors could help inform future missions and space exploration initiatives. Understanding the chemical and physical properties of interstellar objects is crucial for future spacecraft design, as well as for understanding how our solar system fits into the larger galactic context. One of the key takeaways from the study of 3I Atlas is the recognition that the solar system is not an isolated entity, but rather part of a larger galactic environment. Interstellar objects are constantly passing through the solar system, offering a unique opportunity to study the conditions of other star systems and the broader dynamics of the galaxy. As humanity looks
Toward the stars, these objects could serve as markers, pointing the way toward new realms of discovery and exploration. In the coming decades, space agencies like NASA, ESA, and private space organizations may begin to develop missions designed specifically to study interstellar objects up close. Just as the Voyager probes were sent to study the outer reaches of the solar system, future spacecraft might be launched to explore interstellar objects and gather data on their composition, structure, and behavior. These missions would represent a significant leap forward in space exploration, offering insights into the nature of the universe that were previously beyond our reach. Moreover, the arrival of interstellar objects also opens up the possibility of future space travel to other star systems. The discovery of 3I Atlas and other interstellar visitors raises the tantalizing question: could humanity one day venture beyond the solar system to explore the star systems from which these objects originate? The study of 3I Atlas could provide valuable information about the feasibility of interstellar travel, helping scientists design spacecraft and propulsion systems that could one day carry humans to distant stars. As space exploration continues to evolve, the study of interstellar objects will play a key role in shaping our understanding of the universe and our place within it. The arrival of 3I Atlas has challenged our understanding of the solar system and our place in the galaxy. This interstellar visitor has provided new insights into the dynamics of our solar system and the forces that shape the motion of objects across the galaxy. But perhaps the most profound implication of 3I Atlas's passage is the realization that the solar system is not isolated. It is part of a vast, interconnected universe where objects from distant star systems regularly pass through our cosmic neighborhood. The passage of 3I Atlas is just one piece of a much larger cosmic puzzle. It has raised fundamental questions about the nature of space and time, the behavior of objects from other star systems, and the role that these objects play in shaping the evolution of our solar system. As scientists continue to study 3I Atlas and other interstellar visitors, they are uncovering new insights into the workings of the galaxy and the broader universe. The implications of 3I Atlas's passage are far-reaching. As we learn more about these cosmic visitors, we will gain a deeper understanding of the forces that shape the universe and our place within it. And as we continue to explore space, we may find that our solar system is just one small part of a much larger and more complex cosmic landscape, one that is full of mysteries and untold stories waiting to be discovered. The arrival of 3I Atlas, an interstellar object speeding through our solar system, has forced astronomers to reconsider long-held assumptions about how objects from outside the solar system interact with our cosmic neighborhood. For centuries, humanity has viewed the solar system as a relatively stable and isolated region of space, governed by the predictable
Gravitational influence of the Sun. Yet, 3I Atlas's sudden appearance reminded us of how fragile and interconnected the solar system truly is. Interstellar objects are not bound by the Sun's gravitational pull. This means they do not follow the same orbital patterns as the comets, asteroids, and planets within the solar system. Instead, they come from other star systems, often traveling at much higher velocities than those seen in objects that have been gravitationally captured by the Sun. When they enter the solar system, they do so with a unique trajectory and a set of behaviors that are radically different from what we might expect from more familiar solar system bodies. What happens when these objects enter the solar system? Their high velocity and unpredictable paths make them particularly challenging to track, and their brief passage through the solar system raises a host of questions. Unlike comets that are typically on long elliptical orbits and can be predicted with a reasonable degree of certainty, interstellar objects can appear from any direction and on any trajectory. Their arrival is often unpredictable, and by the time we spot them, they have already crossed vast stretches of space, making them difficult to study in depth. For 3I Atlas, its passage through the solar system was a fleeting moment in time. Traveling at incredible speeds, it passed through the Sun's gravitational influence without being captured, continuing its journey out into interstellar space. This one-time visit, however, offered astronomers an unprecedented opportunity to study the object and its interactions with the solar system. Scientists have since worked tirelessly to analyze its chemical composition, its trajectory, and the forces that influenced its movement through the system. What they have learned from 3I Atlas could reshape our understanding of the broader universe and open up new avenues of research on interstellar objects. One of the most interesting aspects of 3I Atlas's passage was its interaction with the solar system's gravity. The Sun's gravitational field had a noticeable effect on the object's trajectory, causing it to speed up as it approached and then slowing down slightly as it passed. The strength of the Sun's gravitational pull also allowed scientists to make observations about how objects from other star systems behave when they enter a gravitational field for the first time. Moreover, the speed at which 3I Atlas was traveling made it clear that the solar system is not a closed system. Interstellar objects like 3I Atlas are reminders that our solar system is just one part of a much larger cosmic neighborhood, and objects from other star systems are constantly passing through it. In fact, it's possible that interstellar visitors have been arriving in our solar system for billions of years, though they were largely unnoticed until advances in technology allowed us to detect them. The arrival of 3I Atlas has also sparked discussions about the future of space exploration and the need for advanced technologies to track and study objects from beyond our solar system. As humanity continues to explore the cosmos, we will undoubtedly encounter more objects like 3I Atlas, and the knowledge gained from studying these objects will play a critical role in shaping the future of space travel.
One of the most significant challenges faced by astronomers in studying 3I Atlas was the difficulty of tracking its path through the solar system. Unlike objects that are gravitationally bound to the Sun, interstellar visitors like 3I Atlas are not confined to the predictable orbits that we are used to. They approach the solar system from any direction and at speeds that far exceed those of planets and comets within the system. The high velocity and unpredictable trajectory of interstellar objects make them incredibly difficult to detect and track. Unlike comets that are often visible months or even years before they pass through the inner solar system, interstellar objects like 3I Atlas often arrive without any prior warning. For astronomers to track them effectively, advanced telescopic surveys and space-based observation systems are required.
The first detection of 3I Atlas came when the object was already relatively close to the solar system, leaving astronomers with limited time to study it before it continued on its journey out of the system. In the case of 3I Atlas, the object's speed, much faster than typical comets or asteroids, meant that it was traveling so quickly that scientists had to work at breakneck speed to gather as much data as possible before it was too late. To track interstellar objects like 3I Atlas, astronomers rely on a combination of ground-based telescopes and space-based observatories. Some of the most important instruments for detecting interstellar objects are large sky surveys, which continuously scan the heavens for potential threats or visitors. These surveys have been designed to detect asteroids and comets, but with the recent discovery of 3I Atlas, the scope of these surveys is expected to expand. One example of an important tool in this effort is the Pan-STARRS, Panoramic Survey Telescope and Rapid Response System, which uses a wide-field optical telescope to scan the sky for objects that may be headed toward the solar system. Pan-STARRS was one of the first instruments to detect 3I Atlas, and its ability to monitor vast areas of the sky will be crucial in the future for spotting other interstellar objects that may pass through the solar system. In addition to Pan-STARRS, other observatories, such as the Large Synoptic Survey Telescope, LSST, and space-based telescopes like the James Webb Space Telescope, will be key to monitoring interstellar objects in the future. These instruments will allow astronomers to study the chemical compositions, trajectories, and other characteristics of interstellar visitors with unprecedented detail. One of the key challenges of tracking interstellar objects like 3I Atlas is their speed. As these objects travel at velocities far greater than typical solar system objects, their paths can be difficult to predict. To improve the accuracy of tracking, scientists are turning to advanced computational models that use a combination of observed data and simulations to predict the future trajectories of these objects. These models are crucial for understanding how interstellar objects behave as they pass through the solar system and how their trajectories may change under the Sun's gravity. The study of 3I Atlas has not only offered astronomers a glimpse into the dynamics of interstellar space, but has also provided valuable insights into the chemical makeup of the universe. One of the most striking features of 3I Atlas was its unusual chemical composition, which was vastly different from what we see in typical comets and asteroids from our own solar system. When 3I Atlas was first detected, scientists quickly realized that it contained an unusually high concentration of carbon dioxide and cyanogen. These compounds, while not inherently dangerous, are rarely found in comets from the solar system. The presence of cyanogen, a molecule consisting of carbon and nitrogen, suggested that 3I Atlas came from a star system with very different conditions from our own. The unusual chemistry of 3I Atlas has raised intriguing questions about the formation of objects in other star systems. Could the conditions in its home system have led to a different mix of chemical compounds than we observe in our solar system? Could 3I Atlas's chemistry provide clues about the building blocks of planets and life in distant galaxies? What is particularly fascinating is that 3I Atlas's chemical composition offers a snapshot of a star system that is billions of years old. The materials that make up 3I Atlas were forged in the conditions of another star system, far from our own, and have been traveling across the vast reaches of interstellar space for millennia. Studying these materials provides astronomers with a rare glimpse into the chemical and physical conditions of a distant system, a window into the past of a star system that no longer exists in the same form. The presence of cyanogen in 3I Atlas is of particular interest because it is a compound that is often associated with the early stages of planetary formation. Cyanogen is made up of carbon and nitrogen, two essential elements in the building blocks of life. Its presence in 3I Atlas raises the possibility that the conditions necessary for life, at least as we understand it, may be more common in the galaxy than we thought.
By studying the chemical composition of 3I Atlas, scientists are gaining valuable insights into the processes that govern the formation of stars and planets. These insights could help refine models of planetary formation, particularly in star systems that are far older than our own. The arrival of 3I Atlas raised important questions about the dynamics of the solar system. Although the object was not on a collision course with Earth, its high velocity and unusual trajectory led scientists to consider how its passage might influence the solar system's gravitational environment. Could an object like 3I Atlas cause subtle shifts in the orbits of planets, moons, or smaller bodies in the solar system? Gravitational interactions between objects are a fundamental aspect of the universe. The Sun's gravity governs the motion of the planets, while the gravity of massive planets like Jupiter has a significant effect on smaller bodies such as asteroids and comets. However, 3I Atlas, with its high speed and hyperbolic trajectory, presented a new challenge for scientists. Could it be that
Its passage through the solar system, even at a distance, could cause small but noticeable shifts in the orbits of other objects? The gravitational influence of 3I Atlas would be much weaker than that of the Sun or Jupiter. However, given the sheer velocity of the object, the small gravitational effects it could exert on other objects might accumulate over time. In particular, scientists wondered if the gravitational influence of 3I Atlas could nudge comets or asteroids from their stable orbits, potentially sending them on a collision course with other planets or moons. While 3I Atlas did not pose an immediate threat to Earth, its passage raised questions about the long-term effects of interstellar objects on the solar system's dynamics. Could future interstellar visitors have a more substantial impact on the orbits of smaller bodies? And if so, what measures can be taken to mitigate any potential risks? Understanding how interstellar objects interact with the solar system's gravitational field is a crucial part of planning for future encounters. As astronomers track more interstellar objects in the coming years, they will need to take into account the subtle gravitational influences these objects may have on the solar system's stability. The passage of 3I Atlas through the solar system has raised an important question. Is this object part of a larger, recurring cosmic pattern? Could the arrival of interstellar objects be a regular occurrence, with objects from other star systems entering our solar system on a cyclical basis? For many years, astronomers have studied the movements of objects within the solar system, assuming that the solar system was a self-contained system with limited interaction with other star systems. However, the discovery of 3I Atlas suggests that our solar system is not as isolated as we once thought. Interstellar objects regularly pass through our solar neighborhood, and the conditions that lead to their arrival could be part of a larger galactic cycle. Could the arrival of 3I Atlas be the first of many interstellar visitors? Could other star systems, just like ours, be home to objects that will one day travel through the solar system? The idea that our solar system is part of a larger cosmic cycle is one that challenges traditional ideas about the isolation of our solar system. It raises questions about the future of space exploration and the potential for future encounters with objects from distant stars. If 3I Atlas is part of a larger interstellar pattern, humanity will need to develop the tools and technologies necessary to track and study these objects. The study of interstellar objects could become one of the most important areas of space exploration in the years to come, offering new insights into the origins of the galaxy, the nature of distant star systems, and the possibility of life beyond Earth. One of the most fascinating aspects of the arrival of 3I Atlas was the way in which it interacted with the solar system's primary force, the Sun. While the object's high velocity and interstellar origin ensured it would not remain bound to the Sun's gravity, its brief passage through the solar system nonetheless had significant interactions with the Sun's solar wind and electromagnetic field.
As 3I Atlas entered the solar system, it passed through the Sun's heliosphere, the bubble of solar wind and magnetic fields that extends far beyond the orbit of Pluto. The solar wind, a constant stream of charged particles emitted by the Sun, is a key element in shaping the environment of our solar system. When comets and asteroids pass through the solar wind, they experience changes in their behavior. Their tails form and extend in response to the solar wind's pressure, and their gases become ionized, creating a visible coma. For interstellar objects like 3I Atlas, this interaction with the solar wind could provide vital clues about the object's composition and structure. What made 3I Atlas unique, however, was its speed and the fact that it wasn't gravitationally bound to the Sun. As it entered the solar system at an incredible velocity, 3I Atlas had to contend with the solar wind's forces in a way that no object from within the solar system ever had. The interaction between 3I Atlas and the solar wind could tell scientists more about the object's surface composition and internal structure, providing clues about the conditions in its home star system. Despite its brief interaction with the Sun's wind, 3I Atlas exhibited some typical comet-like behavior, forming a coma and developing a tail, which scientists used to measure its rate of sublimation. However, unlike typical solar system comets, which have a relatively long history of interaction with the Sun, 3I Atlas had never been influenced by the solar wind before, and its outgassing rate was notably different from what astronomers expected. Its behavior challenged established models of cometary interactions with the solar wind, adding a new layer of complexity to our understanding of how objects from other star systems might react in the presence of the Sun's influence. The solar wind, which is responsible for shaping the tails of comets and the overall behavior of interplanetary particles, interacts with any object that ventures into the solar system. As 3I Atlas passed through, its coma began to develop a complex structure, with a tail that grew longer as it approached the Sun. This was due to the intense pressure from the solar wind, which swept the gas and dust from the object's surface. The tail of 3I Atlas was a direct result of this interaction and gave astronomers a unique opportunity to study how an interstellar object behaves when subjected to the solar wind. The interaction with the solar wind also allowed scientists to observe the chemical composition of 3I Atlas in more detail. As it approached the Sun, the object's icy surface began to vaporize, releasing gases that were analyzed for clues about the object's origins. This process, known as sublimation, is typical of comets, but the chemical composition of 3I Atlas was unusual compared to typical solar system comets. The presence of compounds like cyanogen and carbon dioxide in 3I Atlas's coma raised new questions about the chemical diversity of interstellar objects and the potential for other star systems to harbor the building blocks of life.
The interstellar nature of 3I Atlas offered an unprecedented opportunity to study an object that had originated far outside the solar system. While most comets and asteroids in our solar system are thought to have formed in the Oort cloud or Kuiper belt, 3I Atlas came from a completely different stellar environment, one that we can only speculate about. The object's chemical composition and trajectory provided crucial clues about the conditions that existed in the star system from which it originated. One of the most surprising discoveries was the high concentration of carbon dioxide in the object's coma. While carbon dioxide is a common component in comets from our solar system, it is typically found in much lower concentrations compared to compounds like water ice. In 3I Atlas, however, carbon dioxide appeared to be a dominant chemical compound, suggesting that the conditions in its home star system were very different from those in the solar system. This raised questions about how stars form and how the planets around them are created. Another key aspect of 3I Atlas's chemical makeup was the presence of cyanogen, a compound made up of carbon and nitrogen. Cyanogen is toxic in large quantities, but it is also a key building block for life,
as nitrogen is a vital element in the formation of amino acids and other biological molecules. The discovery of cyanogen in 3I Atlas raised the possibility that this interstellar object could provide clues about the potential for life in other star systems. Could cyanogen, along with other organic compounds found in 3I Atlas, be the ingredients for life elsewhere in the galaxy? The chemical signatures found in 3I Atlas also suggested that its home star system may have been much colder than our own. The higher concentration of carbon dioxide and cyanogen, which form at much lower temperatures than water ice, suggests that 3I Atlas formed in a star system that was farther from its host star, in a region where temperatures were low enough for these compounds to condense and freeze. This adds a new layer of complexity to our understanding of how planets and comets form around stars, and raises the possibility that our solar system may not be as unique as we once thought. By studying 3I Atlas, scientists are able to learn more about the types of environments that exist in other star systems. These insights can help astronomers refine models of planetary formation and improve our understanding of how stars and their planets develop over time. The study of interstellar objects like 3I Atlas also allows scientists to test the theory that the solar system is part of a larger galactic network of stars, with interstellar objects frequently passing through, potentially bringing new materials, chemical compounds, and even life to our system. The arrival of 3I Atlas also highlighted the importance of developing more robust detection systems to track interstellar objects. Unlike comets and asteroids that orbit the Sun and are relatively easy to predict, interstellar objects like 3I Atlas can come from any direction, at any speed, and can be incredibly difficult to detect early enough to study them in detail. In the case of 3I Atlas, its speed was one of the key challenges for astronomers. Moving much faster than typical solar system objects, 3I Atlas was nearly impossible to detect until it had already entered the solar system. This late detection left scientists with limited time to study the object.
Before it passed by the Sun and continued its journey interstellar space. As a result, astronomers had to scramble to gather as much data as possible, using telescopes and other instruments to observe the object's behavior and composition. The late detection of 3I Atlas is a reminder that the solar system is not isolated, and objects from beyond the system can appear without warning. This unpredictability has major implications for the future of space exploration and planetary defense. If interstellar objects are more common than we realize, scientists will need to develop better detection systems to identify them earlier in their journey. This would give astronomers the time they need to study these objects in greater detail and, if necessary, plan for any potential threats. One potential solution to this problem is the use of space-based telescopes that can continuously monitor the sky for interstellar objects. These telescopes would be positioned outside Earth's atmosphere, allowing for clearer, uninterrupted views of space. Additionally, the use of artificial intelligence, AI, and machine learning could help process the data collected by these telescopes, making it easier to identify interstellar objects and track their movements. With more advanced detection systems, scientists could potentially spot objects like 3I Atlas long before they enter the solar system, allowing for a more comprehensive study. Moreover, space agencies around the world are already collaborating to develop new technologies for planetary defense, including systems designed to track and intercept objects that pose a threat to Earth. While 3I Atlas did not pose an immediate danger, its passage serves as a stark reminder of the vulnerability of our planet to unexpected cosmic events. The study of objects like 3I Atlas will play a key role in improving our ability to detect and respond to potential threats. The passage of 3I Atlas is not just a one-time event. It serves as a valuable learning experience for scientists and space agencies around the world.
The study of 3I Atlas and other interstellar objects offers a unique opportunity to learn more about the universe and our place in it. By studying interstellar objects, astronomers can refine their models of how planetary systems form, how stars evolve, and how objects from other star systems interact with our solar system. These insights will help us better understand the dynamics of the galaxy and the broader forces that shape the behavior of objects in space. In the future, the study of interstellar objects will also play a critical role in space exploration. As humanity looks beyond the solar system and plans for missions to distant stars, the knowledge gained from studying objects like 3I Atlas will help inform spacecraft design, mission planning, and the development of technologies for deep space exploration. Understanding the behavior of interstellar objects will allow us to design better spacecraft that can handle the harsh conditions of interstellar space, ensuring that we are prepared for the challenges of exploring the stars. Moreover, the discovery of 3I Atlas raises important questions about the potential for life beyond Earth. Could interstellar objects, with their unique chemical compositions, carry the building blocks of life? Could the materials found in these objects serve as the foundation for life in other star systems? The study of interstellar visitors like 3I Atlas may one day lead to breakthroughs in our understanding of the origins of life and the possibility of life elsewhere in the galaxy. As scientists continue to study 3I Atlas and other interstellar objects, they will gain valuable insights that could shape the future of space exploration and our understanding of the universe. These cosmic wanderers may be the key to unlocking new mysteries about the galaxy and may one day help us answer some of the most fundamental questions about life, the universe, and everything in between. As the study of 3I Atlas and other interstellar objects progresses, we are entering a new era in astronomy. The arrival of these objects has opened up new possibilities for understanding the galaxy and our place within it. In the coming years, we can expect more interstellar objects to pass through the solar system, providing new opportunities to study the composition, behavior, and dynamics of objects from other star systems. These future visitors will continue to challenge our understanding of space and push the boundaries of current scientific knowledge. By studying these objects, astronomers can gain deeper insights into the formation of stars, planets, and galaxies. They can also learn more about the conditions that lead to the development of life and the potential for life beyond Earth. The arrival of 3I Atlas has marked the beginning of a new chapter in space exploration. As we continue to track and study interstellar objects, we are not only gaining new knowledge about the universe, but we are also preparing for the next generation of space missions that will take humanity beyond the solar system. The study of these cosmic wanderers will play a pivotal role in shaping the future of astronomy and space exploration for decades to come. The arrival of 3I Atlas was a remarkable event, but it also raised important questions about the solar system's relationship to the broader galaxy. For centuries, astronomers have viewed the solar system as a relatively isolated region of space, governed by the sun's gravitational pull and home to a small collection of planets, moons, and other small bodies. Yet the sudden arrival of 3I Atlas, along with the growing recognition that interstellar objects are capable of entering our solar system, suggests that our solar system is not as isolated as we once believed. Interstellar objects, by their very nature, come from outside the solar system. These objects are not bound to the sun's gravity, and their orbits are not confined to the same predictable paths that govern comets, asteroids, and planets in our system. Instead, interstellar objects pass through the solar system from any direction, often traveling at speeds far greater than those of typical solar system objects. The question then arises, are we constantly being visited by objects from outside our solar system, or is the passage of 3I Atlas a rare event? The more astronomers study these objects, the more they realize that our solar system is far more connected to the greater galactic environment than previously understood. Objects like 3I Atlas may not be as rare as once thought. In fact, they may pass through our cosmic neighborhood much more frequently than we realize.
Scientists are now beginning to consider the possibility that interstellar objects could be a regular occurrence in the solar system. If this is the case, we might expect to see more interstellar visitors in the years and decades to come. While these objects may not pose immediate threats to Earth, their passage through the solar system offers a unique opportunity to study the broader dynamics of the galaxy and our place within it. The idea that we are not isolated in space, but rather part of a larger galactic community, has profound implications for the study of space. It suggests that the solar system is part of a vast, interconnected network of stars and star systems with objects traveling between them over vast distances. This realization could fundamentally change our understanding of the solar system's history and evolution, as well as how we study the broader cosmos. In the coming years, astronomers will be working to develop new tools and technologies to track and study these interstellar visitors. With the help of advanced telescopes and computational models, scientists hope to gain a better understanding of how often interstellar objects pass through the solar system, what types of objects we might encounter, and how these visitors interact with our Sun and planets. The discovery of 3I Atlas came relatively late in its journey, which left astronomers with limited time to study the object as it passed through the solar system. This late detection has raised important questions about the current capabilities of our detection systems and whether they are adequate for identifying interstellar objects before they enter the solar system. Unlike objects that are gravitationally bound to the Sun, interstellar visitors like 3I Atlas can approach the solar system from any direction at any speed. Their trajectories are unpredictable, and their arrival can catch astronomers off guard. For instance, 3I Atlas was detected only after it had already crossed into the solar system's outer reaches, leaving scientists with a narrow window of time to gather data. This late detection was largely due to the high velocity of the object and its approach from a direction that was not well monitored by existing telescopic surveys. The arrival of 3I Atlas has underscored the need for more advanced detection systems capable of identifying interstellar objects earlier in their journey. To effectively track these visitors, astronomers will need to develop telescopes and observational networks that can scan a wider range of space, especially the regions of the sky that are more difficult to monitor from Earth's surface. Space-based telescopes, such as the upcoming James Webb Space Telescope, may play a crucial role in identifying interstellar objects long before they reach the inner solar system. One of the challenges of detecting interstellar objects is that they move much faster than typical solar system objects. While comets and asteroids follow predictable orbits, interstellar objects are free to travel at velocities that can be much higher than the escape velocity of the solar system. This means that once an interstellar object is detected, it may be too late to plan a response. The detection of 3I Atlas was a reminder that even advanced telescopic surveys may not always catch these objects in time.
To address this issue, astronomers are working on enhancing sky surveys, especially those designed to detect objects at greater distances. One approach is to develop telescopes that can scan large areas of space, constantly monitoring the sky for potential threats. These surveys would need to be equipped with powerful sensors and computational models capable of identifying objects based on their velocity and trajectory. In addition, the role of artificial intelligence, AI, and machine learning will be crucial in future detection systems. These technologies can help process the vast amounts of data gathered by telescopes, allowing astronomers to identify interstellar objects more quickly and accurately. AI algorithms could be trained to recognize the unique signatures of interstellar objects, flagging them for further observation. Improved detection systems would give scientists the time they need to study these objects in greater detail and, if necessary, prepare a response. While 3I Atlas did not pose an immediate threat to Earth, future interstellar visitors could potentially be on a collision course with our planet. Detecting such objects earlier would provide more time to assess their potential impact and develop mitigation strategies if needed. The study of interstellar objects like 3I Atlas offers more than just a glimpse into the dynamics of the solar system. It also provides important clues about the broader processes that shape the galaxy. Interstellar objects are like cosmic messengers, carrying information about the conditions and history of other star systems. By studying these objects, scientists can learn about the environments in which they formed and gain insights into the evolution of galaxies, stars, and planets. One of the most exciting possibilities that comes with the study of interstellar objects is the potential for understanding the conditions that lead to the formation of planets and stars in other parts of the galaxy. Objects like 3I Atlas are time capsules, preserving the chemical composition and physical properties of their home star systems. By analyzing the composition of these objects, astronomers can learn about the types of materials that exist in other parts of the galaxy, and how they contribute to the formation of planetary systems. For example, the presence of compounds like cyanogen and carbon dioxide in 3I Atlas suggests that the conditions in its home star system were very different from those in the solar system. These compounds likely formed in a cold, distant region of space, where temperatures were low enough for gases like carbon dioxide to condense into solid ice. By studying the chemical composition of 3I Atlas, scientists can refine their models of planetary formation, gaining a better understanding of how planets and other celestial bodies form in different stellar environments. Interstellar objects also provide valuable information about the physical processes that govern the evolution of stars and galaxies. The movement of 3I Atlas through the solar system, along with its chemical composition, can offer clues about the dynamics of interstellar space, the region between stars that is sparsely populated with gas, dust, and cosmic radiation. These insights can help astronomers better understand the life cycle of stars and the forces that shape galaxies.
In the future, as more interstellar objects are detected, scientists will be able to build a more comprehensive picture of the evolution of the galaxy. By comparing the chemical signatures and physical properties of interstellar objects, astronomers can learn how different types of stars and star systems evolve over time. This knowledge will help us place our own solar system in the larger context of galactic evolution. One of the most intriguing questions raised by the study of 3I Atlas is the possibility that interstellar objects might carry the building blocks of life. The discovery of compounds like cyanogen, along with the high concentrations of carbon dioxide, raises the possibility that these objects could play a role in seeding life in other parts of the galaxy. The idea that life could spread between stars is not a new one. It is known as panspermia, a theory that suggests that life on Earth, and possibly other planets, could have originated from microorganisms that traveled through space on comets or asteroids. While this theory has been debated for years, the arrival of interstellar objects like 3I Atlas provides new evidence that the building blocks of life could indeed travel between star systems, carried on the surfaces of cosmic wanderers. The presence of organic compounds in 3I Atlas, along with its journey through the vast reaches of space, raises the possibility that interstellar objects might act as a medium for the transfer of life's building blocks between stars. If these objects carry the right chemicals and elements, they could theoretically provide the necessary ingredients for life to develop on distant planets. The study of 3I Atlas's chemical composition could help scientists determine whether the compounds found in the object are capable of supporting the formation of life.
In addition to the potential for panspermia, the discovery of life-essential compounds in interstellar objects also raises the possibility that life could exist in other parts of the galaxy, far beyond Earth. If these compounds are common in the universe, it suggests that the conditions for life may be more widespread than we currently understand. The study of interstellar objects like 3I Atlas offers a unique opportunity to explore the potential for life beyond Earth and may one day lead to the discovery of extraterrestrial life. The discovery of 3I Atlas and the growing recognition that interstellar objects are entering our solar system have underscored the importance of international collaboration in space science. The study of these objects is a global effort requiring the collective expertise and resources of scientists and space agencies around the world. The detection and study of interstellar objects like 3I Atlas require advanced telescopes, computational models, and research teams from many different countries. No single nation can bear the entire responsibility of tracking and studying these objects. Instead, it requires the combined efforts of astronomers, space agencies, and governments to share data, collaborate on research, and develop the technologies needed to detect and study interstellar visitors.
As the study of interstellar objects becomes more central to space science, the need for collaboration will only grow. The development of new telescopes and space-based observatories, along with the creation of international data-sharing networks, will be essential for tracking the movements of interstellar objects and studying their composition in detail. Additionally, as planetary defense becomes a more pressing issue, nations around the world will need to work together to develop strategies for dealing with potential threats from objects that come from outside the solar system. The importance of collaboration in space exploration is also evident in the ongoing efforts to expand humanity's reach into space. By working together, countries can pool their resources to tackle the challenges of deep space exploration, planetary defense, and the study of the galaxy. The study of interstellar objects like 3I Atlas is a reminder that space is a shared domain, and humanity's best chance of understanding the universe lies in working together to explore and study it. The arrival of 3I Atlas in our solar system has provided scientists with an unprecedented opportunity to explore the chemical composition of an object from another star system. Unlike anything observed within our own solar system, 3I Atlas carried with it a cocktail of chemical compounds that challenged many of the assumptions held by astronomers about the nature of interstellar matter. One of the most striking aspects of 3I Atlas was its unusual chemical composition. While most comets in our solar system are dominated by water ice, carbon monoxide, and methane, 3I Atlas's coma contained an unusually high concentration of carbon dioxide and cyanogen. This was not entirely unexpected. Carbon dioxide is a common molecule found in many types of comets. But cyanogen, a toxic molecule consisting of carbon and nitrogen, is rarely seen in solar system comets. Its presence in 3I Atlas suggested that the conditions in its home star system were very different from those in our solar system. This raised an intriguing question. What other, unknown chemical processes might be at work in star systems beyond our own? The composition of 3I Atlas is significant not only because of the specific molecules it contains, but also because it offers a snapshot of the environment in which it formed. Interstellar objects like 3I Atlas are essentially time capsules, preserving the chemical signatures of the stars and planetary systems they originated from. By studying the unique mix of chemicals in 3I Atlas, astronomers can learn about the formation conditions of its parent star system, including its temperature, radiation levels, and the types of gases present during its formation. One of the more exciting implications of studying the chemistry of 3I Atlas is that it could provide clues about the diversity of planetary systems across the galaxy. For instance, the presence of cyanogen, a molecule that is highly toxic on Earth, suggests that interstellar objects can carry compounds that are far more complex than what we typically see in comets within our solar system.
This suggests that the building blocks of life, or at least the precursor molecules, could be much more widespread than we thought. Could these objects be seeding other star systems with the basic ingredients for life, just as many scientists believe asteroids did for our own planet?
Moreover, the chemical diversity observed in 3I Atlas challenges traditional models of solar system formation. If the conditions that gave rise to this object differ so much from the solar system's formation, how might this impact our understanding of planetary evolution? Could other star systems harbor planets and moons with the same or even more complex chemistry, which could one day be studied by future space missions? In studying 3I Atlas, astronomers are not just learning about this one particular object, they are also gaining a deeper understanding of the broader processes of star and planet formation that govern the universe. The unique chemistry of 3I Atlas provides a powerful reminder of how much we still have to learn about the diversity of worlds beyond our own. The arrival of 3I Atlas has implications far beyond our understanding of the solar system and planetary formation. The encounter with this interstellar object highlights the potential for future space missions aimed at studying objects from outside our solar system. While the detection and study of 3I Atlas was a rare and extraordinary event, it points to the possibilities of even more discoveries in the future. One of the most immediate questions arising from 3I Atlas's passage is, could we send a mission to study an interstellar object up close? Currently, most space missions are designed to explore objects within our solar system, such as planets, moons, and comets. However, 3I Atlas has demonstrated that interstellar objects can be just as interesting, if not more so, for scientific study. Their unique chemical compositions, high velocities, and trajectories make them an exciting target for future exploration. The idea of sending a spacecraft to study an interstellar object in detail is both daunting and exciting. These objects are moving at such high speeds that capturing one would be a significant challenge. Unlike the relatively predictable paths of comets and asteroids, interstellar objects like 3I Atlas travel along trajectories that are influenced by a number of factors, including the gravitational influence of the Sun and other celestial bodies, as well as the object's inherent velocity. To study an interstellar object up close, a spacecraft would need to be launched years, if not decades, before the object's arrival. In many ways, studying interstellar objects presents a unique challenge. Current spacecraft are not designed to intercept objects moving at the high velocities seen in 3I Atlas and similar visitors. The high speed of interstellar objects means that any space mission aimed at intercepting such objects would require advanced propulsion technology, such as ion drives or even concepts like solar sails or nuclear propulsion. These technologies, while still in development, may hold the key to enabling future missions to study interstellar objects in person. If missions to interstellar objects become a reality, it would open up a whole new frontier in space exploration. Just as the Voyager probes have provided humanity with unprecedented views of the outer solar system, missions to interstellar objects could provide a wealth of new data on the nature of interstellar space, the chemical compositions of far-flung star systems, and the conditions that lead to the formation of planets and life beyond Earth. While the passage of 3I Atlas did not pose an immediate threat to Earth, the increasing recognition of interstellar objects passing through the solar system raises important questions about planetary defense. As we continue to detect and study more interstellar visitors, it's crucial to consider the potential risks these objects may pose to our planet. The vast majority of interstellar objects, like 3I Atlas, pass through the solar system without causing harm. Their trajectories are generally not on a collision course with Earth, and their brief passage through the system typically doesn't result in any direct impact on our planet. However, as these objects are unpredictable in their paths and velocities, the risk of a future interstellar object coming into Earth's direct path cannot be entirely ruled out.
What if an interstellar object traveling at high speed were to hit Earth? The consequences would depend on the size of the object, its speed, and its composition. A small object, such as a meteorite or comet, would likely burn up in the atmosphere, causing little to no damage. However, a large object with a significant mass could cause widespread destruction, similar to the impact events that have occurred throughout Earth's history. To prepare for potential threats from interstellar objects, scientists are considering a range of planetary defense strategies. One possibility is to develop early warning systems that can detect these objects as they approach the solar system. As we saw with 3I Atlas, the earlier an object can be detected, the more time there is to assess the risk and formulate a response. By identifying interstellar objects at greater distances, we could develop better methods for deflecting or avoiding potential impacts. The next step in planetary defense may involve technologies capable of altering the trajectories of incoming interstellar objects. In theory, this could be achieved through methods such as gravitational tractor beams, kinetic impactors, or even nuclear devices. However, these technologies remain in the early stages of development, and much more research is needed before they could be applied to real-world scenarios. Ultimately, the risk posed by interstellar objects remains relatively low at present, but the lessons learned from studying 3I Atlas and other interstellar visitors will help prepare us for future encounters. By investing in planetary defense and advanced detection technologies, we can ensure that humanity is ready to face any potential threats from space. One of the most profound implications of the arrival of 3I Atlas is what it reveals about the nature of the universe itself. The object's long journey through interstellar space, its unexpected arrival in the solar system, and its unique chemical composition all point to a broader, more intricate picture of the cosmos than we have ever fully appreciated. For centuries, humanity has viewed the universe as vast and largely unknowable, but the passage of interstellar objects like 3I Atlas forces us to confront the reality that the universe is full of unseen visitors moving freely between the stars. This realization changes our perspective on space exploration and our understanding of the cosmos.
3I Atlas is a reminder that the universe is far more dynamic than we have traditionally thought. It is not just a collection of stars and planets, but a vast network of interconnected objects, each traveling through space on its own unique journey. The solar system, once thought to be an isolated region of space, is in fact a small part of a much larger galactic community, one that is constantly evolving and changing. The passage of 3I Atlas suggests that objects from other star systems are regularly passing through the solar system, carrying with them information about the conditions and histories of distant galaxies. These objects are time capsules, preserving the chemical signatures of their home star systems, offering glimpses into the processes that shape the universe. The study of interstellar objects is reshaping our understanding of the universe and our place within it. As we learn more about these objects, we will gain a deeper understanding of the forces that govern the formation of stars, planets, and galaxies. We will also learn more about the origins of our solar system and the potential for life beyond Earth. 3I Atlas serves as a reminder that the universe is not a static, unchanging expanse. It is a dynamic, ever-evolving system full of surprises and discoveries waiting to be made. As we continue to study interstellar objects and explore the vastness of space, we are slowly uncovering the hidden mysteries of the cosmos. The discovery of 3I Atlas and the increasing likelihood of future interstellar visitors mark a new chapter in the history of space exploration. As our understanding of the universe continues to expand, so too does the potential for new discoveries and breakthroughs in science and technology. The arrival of 3I Atlas has sparked renewed interest in interstellar exploration.
While human space missions have traditionally focused on the exploration of our solar system, the study of objects like 3I Atlas opens the door to new possibilities. If we can learn to track and study interstellar objects, we may one day be able to explore distant star systems and uncover new information about the origins of the universe and the potential for life beyond Earth. In the near future, space agencies around the world will focus on developing the technologies needed to study interstellar objects in greater detail. This could involve sending probes to study these objects up close, or developing better detection systems to identify them long before they enter the solar system. The study of 3I Atlas has already provided valuable insights into the dynamics of interstellar space, and future missions could build on this knowledge, pushing the boundaries of what we know about the cosmos. Ultimately, the passage of 3I Atlas is just the beginning. As we continue to study these cosmic wanderers, we are taking the first steps toward a deeper understanding of the universe and our place within it. The future of space exploration is filled with infinite possibilities, and the study of interstellar objects will be at the forefront of this new era of discovery.
The arrival of 3I Atlas was more than just an astronomical curiosity. It is a harbinger, a signpost that points toward the larger, more profound mysteries of the galaxy. The object's interstellar origin, its unusual chemical composition, and its trajectory through the solar system provide a glimpse into the broader processes that govern the universe, including the evolution of galaxies, stars, and planetary systems. For decades, scientists have known that our galaxy, the Milky Way, is full of stars, planets, and other objects. However, the vastness of space makes it difficult to observe the full extent of the galaxy's evolution. The solar system, for all its complexity, is a relatively small and isolated part of the Milky Way. Until now, our understanding of the galaxy's evolution has been constrained by the limits of our observational tools. But 3I Atlas's arrival has opened up a new perspective, one that allows us to see beyond our own solar system and catch a glimpse of the galactic landscape that surrounds us. One of the most striking revelations from the study of 3I Atlas is how interconnected the galaxy really is. The presence of interstellar objects suggests that stars, planets, and other cosmic bodies are constantly moving throughout the galaxy, interacting with one another in ways that were previously not well understood. Objects like 3I Atlas, traveling across the vast expanse of space, provide evidence that the galaxy is a dynamic and ever-changing environment. It's not just a collection of isolated star systems. It's a complex, interconnected network of forces and bodies that shape the evolution of the universe. The passage of 3I Atlas also brings into focus the processes that govern the formation of stars and planetary systems. Astronomers have long speculated about the life cycles of stars, how they are born, evolve, and eventually die. What 3I Atlas shows us is that the conditions that create interstellar objects like comets, asteroids, and other bodies extend beyond the confines of any one star system. As objects from one star system travel through the galaxy, they may encounter other stars, potentially triggering the formation of new bodies and even affecting the evolution of other star systems. These interstellar interactions are part of a larger cosmic cycle that governs the life of the galaxy. Ultimately, 3I Atlas serves as a reminder that our solar system is not a static entity, but rather part of a larger galactic ecosystem. The study of such interstellar objects will continue to enhance our understanding of how stars, planets, and galaxies evolve over time. The passage of 3I Atlas through the solar system presents an incredible opportunity not only for scientific discovery, but also for the future of space exploration.
For decades, humanity has focused on exploring our own solar system, sending probes and rovers to study planets, moons, and asteroids. But the arrival of 3I Atlas raises the tantalizing possibility that humanity could one day venture beyond the solar system and explore the stars themselves. The study of 3I Atlas has already revealed valuable insights into how interstellar objects behave as they move through space. By studying its trajectory, velocity, and composition, astronomers have been able to gain a better understanding of the forces at play in interstellar space. But these discoveries are just the beginning. The fact that 3I Atlas was able to travel across
Interstellar space and reach the solar system suggests that there are forces and dynamics at work in the galaxy that we are only beginning to understand. Looking ahead, the study of objects like 3I Atlas could play a key role in advancing humanity's efforts to explore interstellar space. As we develop the technology to study these objects, we will also be laying the groundwork for future space missions that could one day take humans beyond the solar system. The challenges of interstellar exploration are immense, but the lessons learned from 3I Atlas and other interstellar objects will be crucial in developing the technologies needed for long-term space travel. One of the most important lessons we can learn from 3I Atlas is the need for more advanced propulsion systems. Current spacecraft are designed to travel within the solar system, but they are not equipped for the long journey to the stars. To explore interstellar space, we will need to develop spacecraft capable of traveling at speeds much higher than those achievable by current technology. Concepts like nuclear propulsion, ion drives, and even more advanced technologies such as solar sails could play a crucial role in making interstellar travel a reality. In addition to propulsion technology, we will also need to develop better ways to protect astronauts from the dangers of deep space. The interstellar medium, the vast, mostly empty space between stars, is filled with cosmic radiation, high-energy particles, and other hazards. Future space missions will need to incorporate advanced shielding and radiation protection systems to ensure the safety of astronauts on long-duration missions. The study of interstellar objects like 3I Atlas will help us understand the environmental conditions of interstellar space and guide the development of technologies to protect future explorers. 3I Atlas and the broader field of interstellar exploration also raises profound philosophical questions. If we are able to travel to distant star systems, what will we find? Could we discover other forms of life? Could there be civilizations out there waiting to be discovered? The search for answers to these questions will shape the future of space exploration for generations to come. While 3I Atlas's passage through the solar system did not pose a direct threat to Earth, the question of whether interstellar objects can influence the stability of the solar system remains an important topic. The gravitational influence of 3I Atlas on the solar system was subtle, but it nonetheless raises interesting questions about how objects from outside the system interact with our solar environment. As 3I Atlas passed through the solar system, it did experience a gravitational interaction with the Sun. This interaction caused the object to speed up as it approached the Sun and then slow down as it moved away. While these changes in speed were relatively small, they were enough to alter the object's trajectory and velocity. This is typical of the way that gravitational forces work in the solar system. Every object that passes through the system is affected by the Sun's gravity to some extent.
But what if an interstellar object like 3I Atlas were to enter the solar system on a more direct collision course with one of the planets? Could the gravitational interaction between the object and the planet cause significant changes in the orbits of other bodies in the solar system? The answer, as it turns out, is complicated. The Sun's gravitational pull dominates the solar system,
But objects like 3I Atlas, which are much smaller than the Sun and planets, would have only a minor influence on the orbits of the planets and moons. However, over long periods of time, the cumulative effect of many interstellar objects passing through the solar system could potentially cause shifts in the orbits of smaller bodies like asteroids and comets. These shifts could have implications for the stability of the solar system, particularly if a large number of objects with high velocities passed through the system over an extended period. The more frequent the passage of interstellar objects, the greater the chance that their gravitational interactions could affect the trajectories of objects in the Oort cloud, the asteroid belt, and other regions of space. While 3I Atlas did not pose a direct threat to Earth, future interstellar objects may be capable of affecting the solar system's stability in ways that are difficult to predict. These potential effects, however, highlight the need for further research into the gravitational influence of interstellar objects and the long-term consequences of their passage through the solar system. One of the most fascinating questions raised by the arrival of 3I Atlas and other interstellar objects is the possibility that these objects could be carrying signals or messages from other civilizations. While 3I Atlas itself was a natural object, the idea that interstellar objects could potentially carry artificial signals has intrigued scientists and astronomers for decades. Could we one day detect signals from advanced civilizations that have sent probes or even ships across the galaxy? The concept of interstellar communication is not new. Scientists have long speculated about the possibility of receiving messages from extraterrestrial civilizations. However, the discovery of interstellar objects has brought a new dimension to this conversation. If civilizations from other star systems are capable of building spacecraft or probes that can travel between the stars, it raises the intriguing possibility that these objects might carry signals, either intentionally or unintentionally, to other civilizations. While there is no evidence to suggest that 3I Atlas is anything but a natural object, its arrival raises questions about how we would detect interstellar signals should they exist. The detection of signals from other star systems would require advanced telescopes and listening devices capable of picking up faint radio signals or other forms of communication traveling through interstellar space. In addition, the possibility of receiving signals from advanced civilizations would require the development of new techniques for interpreting these signals, much of which remains theoretical at this stage. The discovery of 3I Atlas has prompted some astronomers to think about the future of cosmic communication in new ways. If we can detect and track interstellar objects like 3I Atlas, could we also develop methods for sending signals to other star systems? The study of interstellar
objects is opening up new avenues of thought for researchers who are exploring the potential for interstellar communication and the possibility, but we are not alone in the galaxy. Perhaps the most profound question that 3I Atlas's arrival raises is the possibility of extraterrestrial life. The object's unique chemical composition and the presence of complex organic compounds like cyanogen and carbon dioxide have led some scientists to speculate that interstellar objects could be carriers of life's building blocks, potentially offering clues about the existence of life elsewhere in the galaxy. The discovery of complex molecules in 3I Atlas suggests that the basic ingredients for life could be more widespread than previously thought. Cyanogen, while toxic to humans, is also a key molecule in the formation of amino acids and other organic compounds, which are the building blocks of life. The presence of these compounds in 3I Atlas raises the tantalizing possibility that life could exist on other planets, perhaps in star systems that are far older or colder than our own. Could 3I Atlas and other interstellar objects be part of a larger process of panspermia, the hypothesis that life spreads across the galaxy by hitching rides on comets, asteroids, and other celestial bodies? If so, 3I Atlas could provide us with new insights into the origins of life on Earth and the potential for life on planets in distant star systems. While it is still too early to draw any definitive conclusions, the study of interstellar objects offers an exciting new avenue for exploring the potential for life beyond Earth. The passage of 3I Atlas through our solar system was not just a rare astronomical event. It also illustrated the significant challenges and opportunities that await humanity in the future of space exploration. For centuries, humans have dreamed of exploring the stars, but space travel has been confined largely to our own solar system. The advent of interstellar objects like 3I Atlas, however, has ignited the question, can we too one day embark on journeys that take us beyond the boundaries of our solar system? Interstellar travel is, without question, one of the most ambitious goals in space exploration. The distances between stars are vast, on the order of light years, and even the fastest spacecraft currently in operation would take tens of thousands of years to reach the nearest star systems. Yet, the passage of interstellar objects like 3I Atlas has sparked renewed interest in the possibilities of interstellar exploration. As these objects demonstrate that it is indeed possible for materials to travel across vast distances through the cold, dark expanse of space. For humanity, following in the footsteps of 3I Atlas would require revolutionary advancements in propulsion technology. Current spacecraft are designed to travel within our solar system, and while they are incredibly efficient within these boundaries, they are not capable of reaching the speeds necessary for interstellar travel. Even with current advancements in ion propulsion, the velocity required to travel across the enormous distances between stars remains far beyond our reach.
The high velocity of 3I Atlas, which traveled at speeds greater than 250,000 miles per hour, is a reminder of the immense scale of space and the forces at play when objects traverse interstellar space. If humanity hopes to follow in the footsteps of interstellar objects like 3I Atlas, we would need to develop propulsion systems that can achieve similar velocities. Potential candidates include nuclear fusion propulsion, antimatter engines, or even speculative concepts such as solar sails, which use the pressure of light to propel spacecraft over long distances. Even with advanced propulsion systems, the challenge of interstellar travel goes beyond velocity. Long-duration missions to other star systems would require spacecraft capable of sustaining human life over extended periods of time. This includes life support systems, radiation shielding, and the ability to travel in a sustainable, self-sufficient manner, as resupply missions would be impossible. We would need to develop innovative technologies in spacecraft design, deep space communication, and radiation protection to ensure that any mission to the stars could be successful. Although we are still far from sending humans to other star systems, the study of objects like 3I Atlas provides invaluable data that can inform the future of interstellar exploration. Understanding how interstellar objects interact with the solar system, their chemical composition, and their behavior as they traverse space can help us design spacecraft that are better suited for long-duration missions. Additionally, the more we learn about interstellar objects, the better we will understand the risks and opportunities that come with space exploration beyond the solar system. The discovery of 3I Atlas and its surprising passage through the solar system has opened up a new era in our understanding of interstellar objects. While the event itself was extraordinary, it is far from an isolated phenomenon. The question that now arises is, how often do interstellar objects visit our solar system, and how should humanity prepare for the next one? As 3I Atlas's passage showed, interstellar objects are not bound by the Sun's gravity, and they can approach our solar system from any direction and at any speed. While 3I Atlas is the first known interstellar object to be observed with such precision, it is possible that similar objects have passed through the solar system unnoticed.
With advancements in detection technology and improved observational techniques, it is likely that astronomers will discover more interstellar visitors in the future. The question is not when they will come, but when and how we will be prepared to study and possibly interact with them. The study of 3I Atlas has made it clear that our current observational capabilities are not enough to detect these objects early enough for a detailed study. By the time 3I Atlas was discovered, it had already passed through the outer reaches of the solar system. If we are to better prepare for future interstellar visitors, we will need to develop more advanced systems to detect objects at much greater distances. One promising area of research is the use of space-based telescopes to monitor deep space for interstellar objects. Ground-based observatories, while effective in monitoring objects within the solar system, are limited by Earth's atmosphere, which distorts observations and limits the field.
A view. Space-based telescopes, on the other hand, can observe the vast reaches of interstellar space with greater clarity, providing astronomers with the ability to detect objects like 3I Atlas long before they reach the inner solar system. Instruments like the upcoming James Webb Space Telescope, which is designed to observe the farthest reaches of space in infrared wavelengths, will play a key role in identifying and studying these objects in the future. In addition to improving detection, humanity will need to develop the infrastructure and tools to study these interstellar visitors. The study of 3I Atlas has already provided astronomers with valuable information about the object's trajectory and chemical composition, but future interstellar visitors may be more challenging to study. A more extensive network of space-based observatories, combined with the power of artificial intelligence, AI, and machine learning, could help astronomers process and analyze the vast amounts of data generated by these objects. The potential for future interstellar visitors presents not only scientific opportunities but also challenges. While the chances of an interstellar object colliding with Earth are incredibly small, the discovery of 3I Atlas has highlighted the need to develop a planetary defense strategy that accounts for these types of objects. Understanding how these objects behave, tracking their trajectories, and determining their potential risks will be crucial for safeguarding Earth in the future. The passage of 3I Atlas through the solar system has sparked renewed interest in one of the most profound questions in science. Are we alone in the universe? While 3I Atlas itself is a natural object, its composition and the materials it carried with it raise the possibility that interstellar objects could play a role in the spread of life across the galaxy. The study of 3I Atlas revealed that the object contained complex organic compounds such as cyanogen and carbon dioxide, chemicals that are not only important for understanding the object's formation, but could also be key ingredients for life. Cyanogen, in particular, is a molecule composed of carbon and nitrogen, two elements that are crucial for the formation of amino acids, proteins, and other biological molecules. While cyanogen is toxic in high concentrations, its presence in 3I Atlas raises intriguing questions about the potential for life elsewhere in the galaxy. The idea that life could spread across the galaxy via interstellar objects is known as the panspermia hypothesis. According to this theory, life's building blocks, amino acids, nucleotides, and other essential compounds, could be carried from one star system to another on comets, asteroids, or other celestial bodies. Over billions of years, these objects could deliver the necessary ingredients for life to form on planets around other stars. While the panspermia hypothesis remains speculative, the discovery of organic molecules like cyanogen in 3I Atlas lends support to the idea that the building blocks of life may be common throughout the galaxy. The fact that these molecules were present in an object that traveled from another star system suggests that the conditions necessary for life might not be as rare as we once thought. If interstellar objects like 3I Atlas can carry the ingredients for life across the galaxy, it raises the possibility that life may exist on planets in distant star systems. This discovery has profound implications for the search for extraterrestrial life.
The study of interstellar objects may one day help us understand how life began on Earth and whether it could have arisen independently on other worlds. The passage of 3I Atlas serves as a reminder that the universe is far more interconnected than we ever realized. If life's building blocks can travel between stars, then the potential for life to exist on other planets may be far more widespread than we thought. In the coming years, astronomers will continue to study interstellar objects like 3I Atlas in the hopes of unlocking the mysteries of life beyond Earth. The arrival of 3I Atlas has underscored the need for more advanced technologies to detect and track interstellar objects. While current observational systems are designed to monitor objects within the solar system, the unpredictable nature of interstellar objects like 3I Atlas presents unique challenges for scientists. To overcome these challenges, artificial intelligence, AI, and machine learning are becoming indispensable tools for tracking and analyzing interstellar visitors. AI and machine learning algorithms have already revolutionized many areas of science, including astronomy. These technologies allow astronomers to process vast amounts of data in real time, identifying patterns and anomalies that would be difficult or impossible for humans to detect. In the case of 3I Atlas, AI could have been used to detect the object much earlier in its journey, providing scientists with more time to study its trajectory and composition. AI algorithms are particularly useful for analyzing the enormous data sets generated by telescopes and other observatories. With interstellar objects, the sheer volume of data, combined with the complexity of tracking objects moving at high speeds and on unpredictable paths, makes manual analysis difficult. AI systems can process this data more efficiently and accurately, allowing astronomers to identify potential interstellar visitors with greater precision. Machine learning also has the potential to improve the accuracy of predictions regarding the future trajectories of interstellar objects. By training algorithms on vast datasets of known objects, AI can be used to model the movement of new objects, predicting their paths and calculating the likelihood of potential interactions with the solar system. This can help astronomers anticipate future encounters and better prepare for the arrival of other interstellar visitors. As AI continues to evolve, it will play an increasingly important role in the study of interstellar objects and the future of space exploration. These technologies will not only improve our ability to track interstellar visitors, but also enhance our understanding of the broader universe, helping scientists make sense of the vast amounts of data generated by our expanding exploration of space. The journey of 3I Atlas through the solar system serves as a cosmic messenger, reminding us of the vastness of the universe and the interconnectedness of all things. While the object itself was a natural phenomenon, its passage through our solar system has profound implications for humanity's understanding of the universe and our place within it. For centuries, humans have looked up at the stars, wondering if we are alone in the galaxy. The arrival of 3I Atlas challenges the assumption that our solar system is isolated and self-contained. Interstellar objects like 3I Atlas are not just travelers from distant star systems, they are messengers, carrying with them the potential to unlock the mysteries of the galaxy and the forces that shape the universe. The study of 3I Atlas and other interstellar objects opens up new possibilities for space exploration, planetary defense, and the search for extraterrestrial life. As we develop the technologies to detect and track these objects, we are also taking the first steps toward exploring the stars themselves. The study of interstellar objects is pushing the boundaries of science and technology, and it is helping us understand the true scale of the universe in ways we never thought possible. In the future, humanity will continue to study objects like 3I Atlas, learning more about the cosmic forces at work and uncovering the hidden mysteries of the galaxy. The arrival of 3I Atlas is just the beginning. As we explore the vast reaches of space, we are only scratching the surface of what the universe has to offer. The arrival of 3I Atlas has far-reaching implications for humanity's understanding of the universe, as it opens up new avenues of exploration, inquiry, and scientific understanding. Prior to its detection, the concept of interstellar visitors seemed like a rare, almost theoretical occurrence. Yet the high-profile arrival of 3I Atlas has shaken that perception to its core, revealing how interconnected and dynamic the universe truly is. As the first confirmed interstellar object to pass through the solar system, 3I Atlas serves as a key milestone that will reshape the way we view our solar system, our galaxy, and the nature of space exploration as a whole. In many ways, 3I Atlas has shown us that the solar system is not an isolated, static region of space, but part of a vast, dynamic system of objects moving between the stars. Interstellar objects, which have traveled across enormous distances from distant star systems, remind us of how much is out there beyond our small corner of the universe. While the arrival of 3I Atlas was a relatively brief event, it marks the beginning of a new era in astronomy and space exploration. For centuries, astronomers believed that stars and planets formed in isolated systems with little interaction between them. The arrival of 3I Atlas has dispelled that notion, suggesting that objects from other star systems are far more common than previously thought. As more interstellar objects are discovered and studied, scientists will continue to refine their models of stellar evolution, planetary formation, and galactic dynamics. The data gleaned from studying objects like 3I Atlas will be invaluable in understanding the broader cosmic processes at work. This new perspective on the universe will also have profound effects on space exploration. The recognition that the solar system is not an isolated bubble, but rather a part of a larger galactic ecosystem, opens up a wealth of possibilities for future space missions. It suggests that humanity is not alone in the cosmos, and that the exploration of space extends far beyond the boundaries of our own solar system. As we look toward the stars, 3I Atlas's arrival has reminded us that the universe is full of untapped mysteries just waiting to be explored. The passage of 3I Atlas through the solar system has provided an unprecedented opportunity to learn about the conditions of a distant star system. Unlike objects that have been bound to the Sun's gravity, 3I Atlas has traveled across interstellar space, carrying with it a unique record of the conditions in the star system where it was born. This makes it a valuable scientific artifact, one that holds clues to the processes that govern stars, planets, and moons in other parts of the galaxy. One of the most exciting discoveries about 3I Atlas was its chemical composition, which was unlike anything seen in solar system comets. Early observations revealed that the object contained compounds that are rarely found in comets from our solar system, such as cyanogen and carbon dioxide. The presence of these compounds suggests that the conditions in 3I Atlas's home star system were vastly different from those in our solar system. For example, cyanogen is a molecule made up of carbon and nitrogen, both of which are essential building blocks for life. The fact that 3I Atlas contains such materials raises the intriguing possibility that life, at least in some form, may be common throughout the galaxy. The unique chemistry of 3I Atlas also provides valuable insight into the diversity of star systems. While our solar system formed from a mixture of gases and dust in a relatively warm, moderate environment, 3I Atlas's parent system likely had conditions that were much colder and more distant from its host star. These differences in the temperature and chemical composition of the two star systems highlight how varied the conditions for planet and star formation can be. As we study more interstellar objects like 3I Atlas, we will gain a better understanding of how stars form under different conditions and how planetary systems develop in diverse environments. The discovery of unusual compounds in 3I Atlas is also changing our thinking about the formation of life. While the early chemical models of life's origins typically focused on Earth-like environments, the presence of organic molecules in interstellar objects suggests that life's building blocks could be much more widespread than we ever imagined. The compounds found in 3I Atlas may hold the key to understanding how life originated not only on Earth, but also on other planets and moons in the galaxy. Could the materials needed for life exist throughout the universe?
While 3I Atlas did not pose a direct threat to Earth, its arrival raised important questions about planetary defense and the potential risks posed by interstellar objects. The unpredictable nature of these objects makes it difficult to anticipate when they might pass through the solar system, and their high velocities make it challenging to prevent potential collisions. Even though 3I Atlas passed safely through the solar system, future interstellar visitors may not be so fortunate, and it is crucial that humanity begin preparing for the possibility of a direct collision. One of the biggest challenges when it comes to planetary defense is that interstellar objects are inherently difficult to detect. Objects like 3I Atlas can approach the solar system from any direction, and their speed makes it hard to spot them far enough in advance to mount a response. The object's arrival was detected only when it had already crossed into the solar system, and its brief passage left little time for astronomers to fully study it. To prepare for future encounters with interstellar objects, humanity will need to develop better detection systems. One potential solution is to expand the scope of current sky surveys, which primarily focus on monitoring objects already within the solar system. Telescopes and space-based observatories that are designed to detect interstellar objects at much greater distances will be key in improving detection efforts. These systems could allow astronomers to identify potential threats earlier, providing more time to analyze the object's trajectory and determine whether it poses a risk. Even with better detection capabilities, however, the next challenge is how to protect Earth from interstellar objects. Although the chances of an impact are small, the consequences of a collision with a high-speed interstellar object could be catastrophic. The sheer velocity of these objects, combined with the potential for them to carry large amounts of kinetic energy, means that they could cause significant damage to Earth if they collide with our planet. The potential risk posed by interstellar objects highlights the need for advanced planetary defense technologies. This could include systems capable of altering the trajectory of an incoming object, such as kinetic impactors, nuclear deflection technologies, or other methods still in the experimental phase. The challenge lies not only in detecting these objects in time, but also in developing the technologies needed to prevent or mitigate any potential impacts. As more interstellar objects are detected, scientists and space agencies will need to collaborate and invest in the research required to ensure that humanity is prepared for future threats. The study of 3I Atlas has shown just how important advanced technology in detecting and analyzing interstellar objects. While the discovery of the object was an incredible achievement, it also underscored the limitations of current systems. As interstellar objects are typically moving at high speeds and arriving from unknown directions, it is essential that we develop more advanced tools and techniques to identify and track these visitors from beyond the solar system. One area where technology is making a significant impact is in the use of artificial intelligence, AI, and machine learning. These technologies allow astronomers to process vast amounts of data quickly and accurately, identifying patterns that would be difficult to detect with the human eye. AI and machine learning are already being used in a variety of fields to analyze large data sets, and their application to astronomy is becoming increasingly important. For interstellar objects like 3I Atlas, AI can play a crucial role in tracking their movements, predicting their future trajectories, and analyzing the data gathered from telescopic observations.
By using machine learning algorithms, astronomers can automate the process of identifying interstellar objects and calculating their paths through space. This would allow for faster identification and give scientists more time to study these objects in detail. AI can also be used to analyze the chemical composition of interstellar objects. When objects like 3I Atlas are discovered, astronomers often collect large amounts of data about their spectral signatures, which provide clues about the elements and compounds that make up the object. AI systems can be used to quickly identify patterns in this data and help astronomers determine the chemical makeup of the object. This is especially important for interstellar objects, as they are often unlike anything seen in our solar system and require careful analysis. Furthermore, AI-powered telescopes could be integrated into the next generation of space-based observatories. These systems would be capable of scanning vast regions of space for potential interstellar visitors, automatically detecting and analyzing objects as they approach the solar system. By combining the power of AI with advanced observational technologies, we can improve our ability to detect, track, and study interstellar objects, providing us with invaluable data on the broader dynamics of the galaxy. As scientists study 3I Atlas, they are not only learning about this particular object, they are also gaining insights into the origins of the solar system itself. The arrival of interstellar objects like 3I Atlas offers a rare opportunity to explore the building blocks of planets and stars in distant star systems, shedding light on the processes that have shaped our own solar system. The composition of 3I Atlas is radically different from that of typical solar system comets. Its high concentration of carbon dioxide and cyanogen suggests that the conditions in its home star system were significantly colder than those in our solar system, which could have led to. The passage of 3I Atlas has forever changed our understanding of the solar system and its relationship to the broader universe. Previously, we viewed the solar system as an isolated system with limited interactions with other stars and galaxies. However, 3I Atlas's interstellar journey through our solar system revealed that our solar neighborhood is far more dynamic and interconnected than we realized. Objects like 3I Atlas are not isolated occurrences, but rather part of an ongoing cosmic process that we are just beginning to understand. This shift in perspective challenges the boundaries of our solar system, suggesting that the space between stars is filled with objects traveling across immense distances. The future will see more interstellar objects passing through, and our understanding of them will evolve as we develop better technologies to track, study, and ultimately understand them. The significance of
3I Atlas lies not only in its passage, but also in the questions it raises about our place in the cosmos and the forces at play beyond our solar system. The study of 3I Atlas doesn't just provide insight into our solar system. It offers a potential roadmap for interstellar exploration. As humanity sets its sights on traveling beyond the solar system, objects like 3I Atlas provide a glimpse into the future of space travel. They demonstrate that interstellar objects can survive the harsh conditions of deep space and travel vast distances across the galaxy, sometimes arriving in our solar system after millions of years. This realization brings into sharp focus the importance of developing advanced propulsion technologies that can handle the immense distances between stars. The technologies required for interstellar travel, such as nuclear propulsion or even concepts like solar sails, are still in the experimental stages. But the need for them is becoming more urgent as we prepare for the next great frontier in space exploration. 3I Atlas's passage highlights how much we still have to learn about the movement and behavior of objects in interstellar space. With improved detection and tracking systems, future missions could study these objects up close, gaining knowledge that will directly inform the development of interstellar spacecraft.
As we enter this new era of interstellar exploration, one of the most significant tools at our disposal will be artificial intelligence, AI. AI and machine learning are already revolutionizing many aspects of space research, from data analysis to predicting celestial phenomena. For interstellar objects like 3I Atlas, AI can play a pivotal role in detecting, tracking, and studying these visitors long before they arrive at our doorstep. AI can be used to analyze the vast amounts of data generated by telescopes and other instruments, helping scientists identify patterns that would be difficult for human observers to detect. For example, machine learning algorithms could process images and spectra from space-based observatories to determine the chemical composition of interstellar objects, track their movements, and predict their potential interactions with the solar system. In addition, AI can be used to create more accurate models of interstellar object trajectories, improving our ability to predict future encounters. As these technologies become more advanced, they will allow astronomers to detect interstellar objects earlier and study them with greater detail. This will also help prepare us for potential future encounters and enable us to respond more effectively. One of the most exciting and profound questions raised by 3I Atlas's passage is the potential for extraterrestrial life. The discovery of organic compounds like cyanogen and carbon dioxide in 3I Atlas opens up new possibilities for understanding how life might arise elsewhere in the galaxy. If interstellar objects like 3I Atlas can carry the building blocks of life, it stands to reason that life could exist on planets around other stars. The concept of panspermia, the idea that life or its building blocks could be transferred between planets and star systems, has long been a topic of scientific speculation.
The presence of complex organic molecules in 3I Atlas suggests that the ingredients for life may be more common than we thought. If these molecules can travel across the galaxy, they could potentially seed other planets with the raw materials necessary for life to form. While 3I Atlas itself is not a direct source of life, its chemical composition serves as a reminder of how interconnected the universe is. The study of objects like 3I Atlas may one day help scientists answer the age-old question of whether we are alone in the universe. The search for life beyond Earth has taken on new urgency, and the discovery of organic compounds in interstellar objects will play a crucial role in this ongoing investigation. The discovery of 3I Atlas and the growing interest in interstellar objects have sparked a new wave of interest in the future of space exploration. While humanity has made great strides in exploring the solar system, the true challenge lies beyond our own cosmic neighborhood. 3I Atlas's passage serves as a reminder of the vastness of space and the challenges we will face in reaching other stars. Interstellar missions are the next logical step in space exploration. The technology to send probes and spacecraft to distant stars is still in its infancy, but the potential to send missions to other star systems is becoming more and more tangible. Just as the Voyager probes have provided invaluable data about the outer reaches of the solar system, future interstellar probes could provide a wealth of knowledge about distant stars and planets. The study of 3I Atlas is providing the groundwork for these future missions. By understanding the behavior of interstellar objects, we can learn how to design spacecraft that can survive the long journey through deep space, including dealing with cosmic radiation, long-term life support, and propulsion over vast distances. Additionally, missions to study interstellar objects could pave the way for the detection of exoplanets in other star systems and perhaps even the discovery of extraterrestrial life. One of the most important questions raised by 3I Atlas is whether we will see more interstellar visitors in the future. While the discovery of 3I Atlas was groundbreaking, it is not the only interstellar object to have entered the solar system.
Prior to 3I Atlas, astronomers detected Oumuamua, a similarly mysterious object that passed through the solar system in 2017. These objects are incredibly rare, but the increasing number of discoveries suggests that more may be out there, waiting to be detected. With advancements in detection technology, astronomers are beginning to find more interstellar objects. The sky surveys that were originally designed to monitor asteroids and comets are now being adapted to search for interstellar visitors from beyond the solar system. As we improve our ability to detect and track objects from beyond the solar system, we may begin to uncover a hidden population of interstellar objects that pass through the solar system far more frequently than we previously thought. The potential for more interstellar visitors raises important questions about how these objects may affect the solar system. While the chances of a collision with Earth are small, each new
A calm and interesting voice reading a scientific topic for sleep. An object that passes through provides valuable data about the nature of interstellar space and the forces at work in other star systems. The study of these objects will continue to inform our understanding of how the galaxy evolves and how objects from different star systems interact with one another. The study of interstellar objects like 3I Atlas underscores the importance of global collaboration in space science. While individual countries and space agencies have made great strides in space exploration, it is only through collaboration that we will be able to tackle the challenges of detecting, studying, and potentially mitigating risks posed by interstellar objects. As more interstellar objects are discovered, it will become increasingly clear that planetary defense, space exploration, and the search for extraterrestrial life are global issues that require the combined efforts of the world's scientific community. Space agencies such as NASA, the European Space Agency, ESA, and other international organizations must work together to share data, pool resources, and develop the technologies necessary to monitor and study objects from outside our solar system. Collaboration will also be key to developing planetary defense strategies for interstellar objects. While the risk posed by these objects is currently low, their potential to cause widespread damage if they were to collide with Earth makes it imperative that nations work together to develop early warning systems and mitigation strategies. The growing recognition of the importance of interstellar objects has already led to greater cooperation among scientists and space agencies, and this trend will only continue as our understanding of the galaxy and its contents evolves. The discovery of 3I Atlas and its significance for space exploration is not just a scientific milestone. It is also an opportunity to inspire the next generation of explorers. As humanity pushes the boundaries of space exploration, it is essential to foster interest and engagement in science, technology, engineering, and mathematics, STEM fields. The study of interstellar objects offers a unique platform for inspiring young minds to pursue careers in space science and technology. Educating the public about the importance of space exploration and the discoveries made by studying objects like 3I Atlas is key to ensuring continued investment in scientific research and space missions. The excitement surrounding 3I Atlas's arrival provides an opportunity to engage with the public and explain the profound implications that interstellar exploration has for humanity's future. Public engagement is also vital for promoting international collaboration in space science. As space becomes more accessible and the opportunities for discovery increase, it is important for the global community to come together to share knowledge, resources, and expertise. By fostering a sense of global cooperation and curiosity about the cosmos, we can ensure that the study of interstellar objects and space exploration as a whole remains a priority for future generations.
As we move closer to the possibility of interstellar exploration, ethical questions will inevitably arise. One of the key questions is whether humanity should actively seek to engage with other star systems, whether through sending probes, signals, or even attempting to communicate with potential extraterrestrial civilizations. The ethics of such endeavors will need to be carefully considered. Should we reach out to distant star systems and attempt to make contact with any civilizations that may exist there? What are the potential risks of interacting with alien civilizations, particularly if they are far more advanced than we are? These questions will be central to the debate about the future of space exploration and the role that humanity should play in the larger cosmic community. In addition to these ethical considerations, there is also the question of how to responsibly explore and study interstellar objects. Should we send missions to study these objects up close, or should we be cautious about disturbing the natural environment of these objects? As we explore interstellar space, it will be important to balance scientific curiosity with respect for the unknown. The passage of 3I Atlas through the solar system marks a pivotal moment in the history of space exploration. It has not only challenged our understanding of the solar system and our place in the galaxy, but has also opened up new possibilities for the future of space exploration. The scientific data gained from studying 3I Atlas will continue to inform our understanding of interstellar space, the formation of stars and planets, and the potential for life beyond Earth. As humanity looks toward the stars, the study of interstellar objects like 3I Atlas will play a key role in shaping the future of space exploration. With advancements in technology and international collaboration, the possibilities for discovery are endless. Interstellar exploration, planetary defense, and the search for extraterrestrial life are just the beginning. The universe is vast, and as we continue to study and explore it, we will unlock new mysteries that will forever change our understanding of the cosmos.